to everyone from different places of the world who have joined MBSC Summit 2022, jointly organized by INCOSE India Chapter, Aeronautical Society of India, and IEEE Bangalore section. Me, Kalpesh Sawant from ZF, Project Manager and Executive Committee member of INCOSE India Chapter.
Hello everyone, I am Neha Tiwari, Systems Engineer at Boeing and Executive Committee member of INCOSE India chapter. On behalf of the organizing committee, I would like to extend all of you very warm welcome to the day 2 of Model-Based Systems Engineering Summit 2022. So we sincerely thank our platinum sponsors, Collins Aerospace, gold sponsors, Capella and MapleSoft, and silver sponsors, Honeywell, Certification Training International, and CATFAM ANSYS for supporting the event. So over to you, Kalpesh, for the instructions.
Thanks, Neha. So can we have slides, please? So on second day of our summit, before we actually start, I would like to remind you about few instructions. In case of you are facing any challenges or any troubles, please go to May I Help You desk, and there are the live chats and other things where you'll be supported with your queries. We also have ask a question chat where if you have any queries or you want any technical support that can be provided. This is a brief agenda for today. We'll be having 4 talks, 1 panel, and sponsors videos. At the end, we'll wrap up our summit with talks of Dr. Prasanna Ramamurthy. Before we actually start for our talks, I would like to invite Dr. Ramakrishna Raman, Chapter Chair for IEEE Bangalore Section Systems Council Chapter. Over to you, Dr. Ramakrishna.
Thank you, Kalpesh. I will share my desktop. Let me know once it's visible.
Yeah, it is there, sir.
Sure. Thank you for the opportunity. Hello, everyone. So I'm going to talk a brief of IEEE and the Systems Council. So I'm the chapter chair for the Systems Council chapter in the Bangalore section. So IEEE at a glance, so IEEE has over 396,000 members from spanning over 160 countries through, and IEEE is divided into 10 geographic regions. So in India, we come under region 10 or R10. Over 100,000 student members and 2,500 plus chapters. And over 3,400 student branches at colleges and universities in over 100 countries. So that's the broad base of IEEE. Plus, there are over 39 technical societies and 7 technical councils. And IEEE Explorer, I'm sure most of you are familiar with. It has over 5 million documents. And plus, there are about 200 transactions, journals, and magazines. And IEEE is well known for sponsoring over 1,600 conferences in 96 countries every year through. And there are also, we also collaborate a lot with very different societies to forward the advancement of technology for the benefit of humanity. And over 500,000 conference attendees are there over here. And actually, if you go to IEEE Explore, over 1,800 conference proceedings are available over in IEEE Explore through. So these are the various technical societies. As you can see, it's broad-based over almost all critical topics ranging from aerospace, circuits, industrial electronics, reliability, power and power electronics, transportation, education, photonics, and so on. And we have 7 councils that span across societies. The Biometrics Councils, CEDA, IEEE Nano, the Sensors Council, the Council on Superconductivity, the RFID Council, and the IEEE Systems Council. So that's a brief context on the IEEE System Council, what I will be talking about. So IEEE System Council will be of,
Recording in progress.
This meeting is being recorded.
We come under the IEEE Bangalore section here. The IEEE Bangalore section has over 10,000 members. We host over 2,000 plus events, and we have about 90 plus student branches. And this section actually won the prestigious MGA Outstanding Large Section Award for twice, right, to 2013 and 2019. And also the Art and Distinguished Large Section Award. So IEEE Systems Council is a council under IEEE for the promotion of systems engineering approaches and practices through. A lot of activities happen under IEEE Systems Council. So I'll talk briefly about some of them. The field of interest spans across system education, system modeling, system simulation, design, development, disposal, deployment, program management, quality assurance, a host of topics are of interest for the IEEE Systems Council. As indicated earlier, it spans across multiple IEEE system societies. In addition, there are specific society level publications such as IEEE System Journal. This is a very seminal journal that covers a broad range of topics of interest for the IEEE systems engineering community. And then we also have other transactions such as IEEE transaction, big data, cloud computing, plus very often look forward newsletter on the IEEE System Council newsletter through. And recently, an IEEE OpenSys Journal of System Engineering has been launched for open access across. A lot of technical committees promote various specific areas under systems such as cyber physical systems, intelligent transportation design, system engineering methods, security and privacy in complex systems, and so on through. So these technical committees, committees are broad groups of interest where multiple people of the common interest come together, and then they debate. They work on standards, on white papers, products, and so on, specifically all around advancing the knowledge and practice of the specific area of interest. Also, there's focus on women in systems engineering, called the WISE. So IEEE System Council has adopted and supports the IEEE Women Engineering Pledge. And IEEE WAE is one of the world leaders in changing the face of engineering through, and has over 20,000 members in 100 countries through. Coming to the Bangalore sections of System Council, so I'm chairing, and the secretary is Dr. Yoga. The treasurer is Shailesh from Texas. And then we have the EXCO members, Abhilash, Dr. Srisha Rao from IIIT Bangalore, Professor Srisha from Manipal Institute of Technology, and Dr. Mohit from NIT Karnataka. So recently the chapter conducted a survey to find the top areas of interest for the practitioners and the academicians on systems engineering. So modeling and simulation and MBSE stood at the top through. So in fact, that was one of the reasons why IEEE is getting actively involved in the summit too. And then complex systems, system of systems, specialty areas for that too. So IEEE Connect is a flagship conference of IEEE Bangalore section. So last year we had over 400 delegates attend that, and we had a track specifically focused on systems engineering, where about 9 papers were presented. Similarly, we are continuing that. So in IEEE Connect 2022, that is this year's edition, we have a specific track on system science and engineering. Dr. Yoga is chairing that track. And currently submissions are closed, but we are going ahead. And we are going ahead with the review of the papers through. And then the internship symposium on AAML. So that was again an area of interest. So we had collaborated with INCOSE and AESI in conducting this symposium last October. And we had the IEEE System Council President, Dr. Vincenzo Piori. He was a patron for the event, and he also delivered the inaugural keynote address. Further, we had special lecture series in Manipal Institute of Technology. So for this year, the System Council is planning a host of activities, including the MBSE Summit, partnering with INCOSE and ASI, as well as a lot of webinars and tech talks. So we have this IEEE Distinguished Lecture Series where we are planning to arrange webinars on specific areas of interest for the systems community. So that in a sense, a quick overview of IEEE System Council. So especially IEEE student members, we invite you to join the Systems Council through your college student branches. A host of events and student connects, including sponsoring projects, hosting webinars in the colleges are also planned through. So we encourage all the students to join the Systems Council and get educated on the systems approaches. And a host of universities abroad also offer systems engineering programs through. As we talked about in the yesterday in the panel, a lot of opportunities for systems engineers is opening up in India. So would encourage specifically the students to explore participation in the systems engineering areas. So with that, I would conclude my brief introduction on IEEE Systems Council, and thanks to the conference organizers for providing this opportunity. Over to you, Neha and Kalpesh.
Thank you, Dr. Ramki. Yeah. Thank you, Dr. Ramki. That was a wonderful overview for the IEEE activities. So we'll start with our first talk for the day. I would like to invite Mr. Kevin Robinson, Head of Blue Water and Chief Engineer at Shoal Group Private Limited. Mr. Tim Carter, Principal System Engineer at Shoal Group Limited. We have an interesting topic for the day, demystifying MBSE for rail acquisition agencies. Over to you, Mr. Kevin and team.
All right, so I'll just try to share my screen. Okay, can everybody see that now?
Yes.
Fantastic. Okay, so the focus of this presentation today is demystifying rail, or demystifying MBSE in a rail environment. And the reason that we've put together this presentation is because model-based system engineering is still a relatively new concept for many in the rail industry. Indeed, even systems engineering is relatively new to many people in the rail industry. And that is a function of how long the rail industry has been around for. And trying to introduce something new, there's a certain amount of inertia in trying to introduce new concepts like MBSE. So the challenge is to articulate the value of MBSE, what it does for people in the industry. So what I'm going to do is walk through this presentation and describe how it is we go about trying to communicate model-based systems engineering for people in the rail industry. Okay, so and I suppose one of the things that does actually make it quite difficult to communicate is the fact that when MBSE is done well, what you do is you manage to avoid issues, and therefore the value of good model-based systems engineering is quite often hidden, right? Because it's all about the problems that you didn't have. So, what we're going to do today in this presentation is to talk about demystifying MBSE, but also compare model-based systems engineering to digital engineering, to building information modeling, which is some of the other concepts that are quite often brought up in a rail engineering environment. And once again, try to emphasize what the advantages are of an MBSE approach. Okay, so the first thing that we do as far as explaining MBSE is first, because systems engineering isn't necessarily widely understood in the rail industry, we go through a brief description of what systems engineering is to the rail industry. And in this case, it's important to understand that in the rail industry, systems engineering is more than just a discipline. It's a methodology. And quite often that's the way that we need to explain it, as a methodology rather than as a separate discipline. And that systems engineers need to work closely with stakeholders, design engineers or designers, and other specialty areas that people are more familiar with in the rail industry, along with project and program managers to help develop a coherent and consistent system design. And this is typically based around, I'm sure most systems engineers' favourite diagram, the V. This is an example of a typical V that we have seen in the transport industry. In general, what we're trying to explain is that systems engineering is taking a top-down approach. Now, this can be sometimes quite a challenge. One of the interesting parts to note about this V, which is something that we've seen quite a lot of in the rail industry, is that engineers will like to work through a concept design fairly early on in the life cycle. Now, to a designer designing a subsystem, or perhaps an architect designing a station, a concept design is looks like essentially a first draft of a detailed design. Meanwhile, as systems engineers, what we want to try and do is make sure that the asset that is being built or designed is going to be fit for purpose, and that appropriate budgets, both performance and financial budgets, are actually assigned to the assets that people are trying to build their first initial drafts of a detailed design for. So the next thing that we need to try and make clear is how SE is different from project management and asset management. And the reason that this is important is because when we talk about systems engineering in general terms, it sounds to people in the rail industry a lot like the same benefits that you would get from good project management and good asset management. In that what we're trying to do is lower the risk early on and maximize functionality and minimize cost, not just over the initial build phase of the life cycle, but also the through life support phase. So how do we compare them? All right. Well, we start by pointing out that we're trying to solve the same problem, but through different lenses. Okay. Asset management focuses on the whole of life performance of the assets for the business, from the concept and making sure that they're looking at procuring the right assets, all the way through to how that asset is maintained throughout life, and then eventually retired, and selecting a well-defined and having a well-defined technical solutions a part of this. Okay, project management focuses on delivering the scope, managing the risks, and making sure that you can deliver a scope and manage all the risks. It's very important to have a well-defined technical solution as well. What we're trying to do with systems engineering is take the problem, making sure it's really well defined, and then decompose it into that technical solution that will help people manage the risk, manage the scope, and provide something that's going to provide good value throughout the entire life cycle. So what we need to explain to people is that all these three areas need to be able to work together to help solve or to help deliver effective rail projects. And this is quite important in an industry, again, where SE is not so well known, where project management and asset management are both well known. So we need to explain to people where we fit in. Okay, so having built that as a grounding, what we can then do is start introducing some of the model-based systems engineering concepts. Okay, so thanks to INCOSE for this definition. So the formalized application of, so MBSE, it's basically the formalized application of modeling to support, without reading through the whole thing, to support engineering throughout the various phases. The important thing here is the modeling. So what do we mean by modeling? Well, what we're talking about is taking an information-centric based approach rather than a document-based approach. So we're holding all the information in a database and generating the documents rather than writing the documents, and therefore having to keep multiple documents up to date. So And when we think about this, this is fairly similar to a number of other disciplines that have moved towards more computerized, database-driven engineering methodologies, like architecture and structural engineering, fluid dynamics. They're all using modern computerized systems, and so MBSE is just the systems engineering equivalent of that. So when we have an information-centric approach, what we have to build, therefore, is a schema of how that information is going to be organized and fit together. Okay, so we're just trying to do systems engineering, but we're trying to be clear about how all the information is actually fitting together, which is slightly different to simply writing a set of specifications and designs and so on. We're being more explicit about how the information traces. So how do we describe the model in terms that are going to be natural and intuitive for people to try and understand? Well, we take almost like we take a fairly simple view of the world with some simple generic looking components. Like we've got some animals there, and some bats, a giraffe, an owl, and a frog. And then what we say is what we're trying to do is we're trying to show people how all the information relates and how the various assets might relate to one another. Define a system boundary, and also identify the things that perhaps are outside the system boundary that we'd like to perhaps keep out of the system boundary, perhaps understand what the interfaces need to be. And again, this is fairly intuitive. You don't need to have a degree in model-based systems engineering to understand that we're talking about information and making sure that we show that the relationships. So that might be a structural point of view. And then the next thing that we might wish to do is explain to people, well, we don't just take a structural view of the world, we also want to have a behavioral viewpoint, which is something that we can enrich the model with a new viewpoint and see things from a new perspective and have that eureka moment, that aha moment where you see something that you didn't ordinarily, that you didn't see before. So in this case, we can see that the bats are providing cake to the owl, and the owl is eating the cake, which is representative of system behavior. And once we do this, we can build up a picture of not just the current system, because most rail projects are in fact brownfields projects. There aren't that many greenfields projects. We can also describe using the same techniques that the future system, and then we can interrogate that model and we can identify what all the differences are. So in this case, the existing system might look a bit like a tortoise, a future system might look a little bit like a hare, and so that in the future there will be no shells, and we can interrogate the model quite quickly and easily to find the delta from current baseline to future baseline, and we can do an impact analysis quite quickly. And that's a powerful thing when you're dealing with a hugely complex system. And then the other thing that's definitely worth pointing out is looking at the model as being something that can help you generate documents quickly, and consistently. So what we like to point out is that we build up the system model with an operational view of the world, pull in lots of information from the various subject matter experts or the designers from the various subsystems, as well as high-level strategy documents. And we can stir that all together into the one system model. And I'll talk a little bit about some examples a bit later about where we've done that, pulled in a strategy level, operations level, and decompose that down to what might need to be done from a technical solution perspective. But once you've done that, you can then start generating a huge range of documents, everything from the customer requirement spec to the system and subsystem requirement specs, all the way through to FAMICAs and so on, from the model using complete and consistent information. what we have also done in the past is we're then able to generate up-to-date versions of operational documentation. So your operational and maintenance concepts as well as architectural information, all from the model. And by presenting it this way, we can show the value. Okay, so I have a few notes there on little pearls of wisdom about MBSE that we use to try to communicate the value of MBSE in the rail world. So we point out the model is the current collective understanding of all the various disciplines. So in rail, you have many different disciplines: signaling, civil engineering, structural engineering, electrical, hydraulics, all trying to work together. And so it's important to have an authoritative source of truth that people can rely upon. We want that model to be able to encompass the system design and specification. In fact, I'd like to see it cover a bit more than that, also the operational view of the world. And it needs to be continuously provided to the various teams so they can see, and it needs to be accessible to the teams so that people can see what the current understanding is. And finally, again, we want to be able to generate the documents from the model rather than have people sitting in front of a keyboard typing into Word. We want to be hitting the magic generate button and produce the documentation from the model in a consistent way. Okay, so essential components of MBSE. Again, MBSE is along with systems engineering is still relatively new concept in rail, so we need to go through and we need to explain some of the components of MBSE so that people can be successful in the application of MBSE in rail. So we point out that we need a well-structured meta model, that schema that I was talking about earlier, showing how all the information fits together. Okay, so that's point one. We also need some representation, some viewpoints that we're able to pull out of the model. Now, this is really important. This point. What we need to be able to do with the model is recognise that the model is there not only to communicate information, but it needs to be the right information presented in the right way to people who need to make design decisions. So we need to identify what the viewpoints are that they need for their project, and we need to be able to present the information in a way that's easily consumable for them. So we need fit for purpose views where we can translate the database of information and collect it together into a view that will help an electrical designer, a signaling engineer, an integration engineer, make the decisions that they need to. And finally, we need to make sure that we take the standard systems engineering processes and we apply the appropriate tweaks to turn the process into a model-based systems engineering process. This is generally not too much. It's more about tailoring to suit the fact that you're using an MBSE methodology. All right. So some of the other concepts that we find that we talk about digital engineering and BIM, and I wanted to try and explain how these concepts are connected with model-based systems engineering. So digital engineering, there is a particular standard that is being written in Australia that I've pulled this definition for digital engineering from. So a collaborative way of working using semantic data management to enable more productive methods of project delivery and asset management. Or in my words, I would say it's about using a computerized engineering environment to help you work more efficiently. And and when you understand that, then you understand that the various sub elements of digital engineering is all about trying to help enable an information-centric approach, regardless of whether you're working in systems engineering or any other discipline of engineering. Okay, so just moving on from there. So BIM, which is codified in ISO 19650, building information modeling, is the process of designing and constructing a building or infrastructure asset using object-based 3D modeling. This particular technology or this particular standard way of looking at the world really has its strength in helping engineers solve the physical complexity and the physical complications and the physical clashes over time. So it's all about bringing together all of the various designs from a physical layout perspective and showing how they integrate. The BIM standard itself allows for a greater number of dimensions than three-dimensional modeling and the physical complexity solving of the problem, to include scheduling, cost, and other information which can help you solve the problem in a temporal perspective. That's actually really important, particularly in the rail industry and in infrastructure projects in general. Quite often the most difficult challenges you face is in the design and construction and integration phase, because you really only get one shot to get it right before it gets very expensive to fix the concrete. MBSE, now I've drawn a few circles on this diagram. These circles are not meant to be definitive boundaries of concepts, but rather indications of where these different areas have their strengths. So MBSE is really strong at the front end of the systems engineering V, whereas BIM is much stronger at the back end. There's an amount of planning for verification and validation activities that happens at the front end of the V. BIM is stronger at capturing the detailed design and making sure things will fit together. And digital engineering is really the concepts that supports both. One from the point of view of the physical design, and the other from the point of view of conceptual design. So, how do we explain what's under the hood for MBSE and what the advantages are over perhaps traditional systems engineering approaches? So I'll try to go through this reasonably quickly. So the first stage in a rail project is business case, developing the business case, or in some other sectors, what might be capability design. So what we're trying to do here is understand the strategic guidance and formalize the operational concept, identify the different scenarios or the operational context in which the project will live, and also identify the operational needs, the critical operational issues and the measures of effectiveness, so the COIs and the MOEs. And then we want to try and formalize this into an operational concept, something that might look a little bit like a document, but in the model it will look like a series of scenarios, sequence diagrams, and so on. And we want to provide, therefore, people the tools for which they can consider the different capability options. So I've just got a couple of diagrams here. I see throughout this summit there's been a bit of a focus on using Capella. I also use Capella from time to time. So what we have here is a description of some of the overall capabilities and how some of the overall capabilities might relate and who's involved. And that helps us identify what some of the goals are of the system. We want to understand how the the various stakeholders might interact during the use of the system being designed. And then we want to understand what that means in terms of the different activities the different groups might undertake, and how they relate to other activities. And what this allows us to do is to start to build up these threads or operational processes through the system that in this diagram here you might see as the blue lines or the red lines, and understand what the interfaces are between them. And that allows us to develop a set of need level requirements. So what are the advantages of this from a rail perspective? Well, what this does is it helps provide that structured way to capture the business goals and missions and relate them to the operational views. Traditionally, this is done in a fairly ad hoc way. Traditionally these sorts of activities are done using subject matter experts and expert opinions. And the problem with that is, without using a structured approach, you tend to end up with gaps, even with the best of experts. Okay, so we've used a structured approach to identify and capture the business goals, trace them down to the operational processes, and then that provides the basis for further analysis. So the next step then is to look at the system as a black box. Okay, so whereas previously we're looking at the operational view, now we'll introduce the concept of the system, and we look at it as purely what is the role of the system, what is the role of the rail line relative to customers, external ticketing systems, power supply, and so on. So we can identify what the functionality is that the system has, what the functionality is that you would expect of customers and other external systems, and therefore what the interfaces are between them. Okay, and all of this should then in the model be traced back up to the operational activities. So you typically take an operational process and then try and identify which of those activities sit within an actor, which sit within the system. And so the scenarios then start to show not just the various actors, but also the system, and you can start to see what the system role is. And this allows us to start doing things like allocating performance budgets, which are, I think, quite important from a rail perspective, particularly when you're talking about trying to move people within a reasonable time frame from wherever their home might be to wherever their employment might be and back again, and various other situations like that.
Mr. Tim?
Yep.
Yeah, I'm sorry to interrupt you. We have 5 minutes left for your talk. 5 minutes left.
I'll be real quick.
Yeah.
Okay.
Thank you.
All right. So the advantages here, additional advantages you have. So we're starting to build up a single consistent source of truth, and we can develop completeness using a forced structured approach. Okay. So what we can then do is start taking a view of the logical architecture, which allows us to break things down in a similar way to the system analysis, but at a level where we can try to identify how the system works rather than how it's built. So we're just taking a conceptual view here, and allows us to specify without specifying the solution. And allows us to start allocating budgets, which is the budgets the designers really need. And we really need to emphasize that point when talking about a rail context. So now all of a sudden we can start to develop executable scenarios. We can identify the reliability, availability, and maintainability, as well as safety and other budgets and risks and so on. So we're able to present, here's a structured methodology. We can then drop down into the physical architecture, so how the system is built rather than how it works. And when we do this, we can start to make specific design choices. We can identify how many stations, but again, have it all traceable back to the logical architecture, so we can maintain some consistency across the entirety of the design. And again, that's a big advantage that it brings. And we can also identify what belongs to which work package. Okay, so continuing on, we can see that we've got completeness of solution, coherence, because we trace all the way up the different layers in the architecture and across to the requirements. This also provides us, and this is a big one for rail, we can, by following the functional threads through the system in the model, we can identify which piece of the system needs to be in place first so that you can perform appropriate testing. And it also provides, as I mentioned before, the basis for verification planning. Okay, so a little bit of MBSE wisdom there. I'll skip past that for the sake of time. Now, there are a couple of examples here that I want to go through very, very quickly. So an example of a brownfield system that we have that we've been involved in, where a brownfields project is replacing legacy signalling systems with a European train control system level 2 signalling and automatic train operation and so on. So the focus of the model needed to be about understanding the new functionality and mapping functionality back to the legacy system so you can understand what needed to change, not just in the system, but also the way that the business operates. All right. So what did the model do? The model captured the existing and proposed future state of the system, but also the existing and future state of the operations. And by tracing everything, we could work out exactly where all the gaps were. And this was then able to be translated into a series of technical solution packages with associated requirements that would represent projects to be undertaken over a period of years. Complexity management. So another project that we've worked on needed to really understand how best to minimize the complexity across interfaces between design and construct packages. And stakeholders needed right information to help them make their decisions depending on who they were. So the model itself focused on interface management. It was tuned to the needs. We built it in such a way that we could present the right viewpoints for contract managers, designers, and asset managers, depending whether they were interested in location, contract package, or subsystem viewpoints. So that was really quite powerful. And again, all those views were consistent. Okay, challenges that we find stovepiping. Again, rail is notorious for stovepiping between different disciplines. People working separately and then uploading data is another another issue, because if people are doing that, then they're not really using the model. Deadline focus. People who quite often projects are focused on their deadlines rather than solving the problem and understanding where they are and solving the problem. And so that can be a challenge in rolling out an MBSE approach, which almost demands knowing where you are and solving the problem. And finally, you need a comprehensive digital engineering plan as a prerequisite to make MBSE work and integrate into all of the other information-centric disciplines. Right, I think I'm out of time. All right.
Yeah.
So do we have time for questions, or do we move on
Yes.
to the next?
No. We have questions for you, Mr. Tim and Kevin. So my first question is, so how do you manage the temporal aspect of system of interest in modeling? The systems are developed, manufactured, and assembled at various places, also where each project is different. So, yeah.
Yep. Okay. So I spoke very briefly about this, but later life cycle benefits, integration. So one of the things that's is critical in rail and is the biggest lesson learned from several projects that I'm aware of is interface management. However, what people actually mean when they're talking about that is correctly sequencing the build of the system overall. So which part needs to be built first so that you can structurally mount the second piece and also test things in a sensible, logical fashion. So when you understand which assets are performing which functions and are relying on which other assets. That taking the model-based approach allows you to very quickly identify what the functional threads are through the entire system and where those threads start. And then you can use information that you have about where the beginning of those functional chains are to help inform your construct and integration and test sequencing. So that's how it can help you manage the temporal aspect of a rail build.
Okay. Yeah, thank you, Tim, for answering these questions. We have another questions for you both. So modern railways are large systems of systems where emergent properties are hard to identify and predict, and interaction within and between systems are complex. So traditional projects delivery in the railways relies mostly on the subject matter experts and their knowledge of existing systems and processes. So how easy it is to adapt MBSE in arriving at optimum solutions?
Yeah, interestingly, I've seen a systems of systems model not so long ago in a particular Australian state. The view that they took was let's build a model for their overall transport network, and they looked at various measures of effectiveness. Such as how quickly people could get from point A to point B, how many people they could shift, what the quality of service would look like, and how the needs will change over some years, what's going to be the cost of that. And so they were able to model the performance of the network over a significant period of time and look at it as a system of systems. And by collecting all of that information from the relevant subject matter experts, but also doing a more structured analysis, they're able to come up with an answer that is quite defensible. Then what you can do is you can take an element of that and you can build, like for example, a single rail line, and then you can build a model around that rail line with external interfaces that identify how that particular rail line will fit into the broader system of systems with respect to the performance that you need today and in the future, and using a number of different measures of effectiveness for that. And then from there, you can then start to identify what the business goals are for it, and then that can then be broken down into, okay, this is what our operations need to look like, and then transition down into your system analysis, et cetera, et cetera. So there's a flow there that works.
Okay. Thank you so much. Thank you so much, Tim and Mr. Kevin, for the insightful talk on the demystifying MBSE for the rail acquisition agencies. Thank you.
Awesome. Thank you so much for your time.
Thank you.
Now coming to our next talk too. So I would like to invite Dr. Sudarshan Rachuri, Technology Manager in Advanced Manufacturing Office, Energy Efficiency and Renewable Energy, and Department of Education. I welcome you, sir.
Okay. Can you hear me?
Yes, I can hear you.
Yeah, it says I cannot share the screen. So can I get the permission to share the screen?
You can share now, sir.
Okay, thank you. So can you see my screen? Let me put in the full mode. So which one are you seeing? Are you seeing the my presentation mode or? Oh. Yeah, I'll swap it. 1 second. So can you see it now? Okay. Thank you. Good afternoon, good evening, or good morning, depending on where you are. I'm in Department of Energy, not Department of Education. So just want to correct that. I saw around 14 or 15 participants. So if you don't mind, Yoga, if you're listening, I want to keep it interactive instead of, asking the questions at the end, because, I can manage 15 people. So please let me know if you want to make it interactive, and I can go and answering the questions as we go along.
Okay, Sudarshan, it is actually, there is another platform where this is going to be streaming. So in this case, we are all just 14 of us, and the questions from that would come into the chat.
Oh, okay.
So then, somebody will tell, and whatever you answer, they will hear, but, the questions will be coming through the chat.
Okay, thank you. Thank you.
Sure.
Okay, good that I'm following the talk by Kevin and Carter. This is about model-based engineering for manufacturing, so especially on smart manufacturing innovation. I'm a senior technology manager at Advanced Manufacturing Office in Department of Energy. I also manage an institute called Clean Energy Smart Manufacturing Innovation Institute, which was funded by DOE. It's around $200 million investment. It's a public-private partnership started 5 years ago. And most of the work is related to how smart manufacturing and bringing IT, information technology, and operational technology to manufacturing. So the way that I want to do it is what is the model, and how models are used or produced. There is a producer of information, and there is a consumer of that information. What are the different ways that they bring a model to their domain of discourse? And Yoga asked me to talk about how standards come into play. What are the type of standards? I will talk about what are the typology of standards that are related to manufacturing and model-based engineering, and especially the intersection between that. I saw a previous talked about meta models. I'll talk about what are the different type of model-driven architectures and MBSE can be used. And then the main talk is about manufacturing. So I'll talk about what are the different types of manufacturing programs that I manage. One is sustainable manufacturing. It's basically about resource efficiency. And smart manufacturing is about how do you bring information technology and operation technology together using machine learning and sensor technologies. And then I'll talk about how we are using domain-specific models in terms of process models and energy and material information. And then finally I'll talk about cyber physical system model of smart manufacturing and how all these elements come together to build that a platform for smart manufacturing, something like an operating system for industrial Internet of Things. And then finally, I'll have some time for closing remarks. I mentioned about a model. It starts from a producer of the information model that they are trying to create about whatever they are trying to represent in the real world, and then the consumer. So both of them have their own mental model of the specific content in a domain of discourse. It could be healthcare, it could be manufacturing, it could be rail system that the other speaker were talking about. That content will have both formal and informal representation of information and conceptual models, and also models related to physics. And the way that we always do a compromise or a trade-off between how expressive that model should be, or the language for representation of the model should be, and how much is computer representable and computationally distractible. So this is always this trade-off. And you can see the different languages, starting from natural language. You can express a lot, but it's very difficult to compute. If you want to do any reasoning or inferencing at that level, it is very difficult. But if you do a structured information all the way up to the programming languages, it becomes much slightly easier in terms of inferencing. So this is all about how we do modeling between two agents. So whether it is whoever is producing and consuming, so the roles can be reversed as their information is exchanged between them. So the representation of the languages, starting all the way from a natural language to programming language, I'll talk about how different structures are very useful for different purposes. So if you take that to manufacturing, it becomes really complex. And I know this is a very busy slide, but I'll walk you through this. If you look at the bottom, there are different stakeholders, the designers, and across the life cycle of manufacturing, all the way to the end of life and the recycling and reuse. And I just mapped that previous slide in terms of producer and consumer, and then expanded it to manufacturing. That's all I made at the top. At the bottom, you can see the different types of information modeling that we need and the conceptual modeling you need. For example, any product that you produce has only three things: form, function, and behavior. Form means structure and materials. Function means what is it supposed to do, what is the intended behavior. And the behavior is actually how the product is performing in the real world. And the process information is basically how the state transition of the product as we go in manufacturing and different steps of the manufacturing process. So there are three types of flows that happens in process: energy flow, material flow, information flow. And one of the other important things that we also look at is the water. Water is an important aspect of manufacturing. And then if you look at the life cycle of information across, different type of information is consumed and produced at different stages of life cycle. But the real challenge is how this information is shared across and make sure that the system thinking can happen. So this is similar to what other people are talking about. You can put the reductionist approach of taking a system and breaking it into different components. But when you start putting it all together, that's where the problem comes. The main reason is when in any conceptual modeling, suppose you take a vehicle, and then you can say car and train or boat, they are all vehicles. But when you look at that, they are this is a vehicle, but they are different vehicles at the different stage, because one is land moving, another is water moving, etc. That discrimination principle between two classes of vehicles is what is missing in many of the conceptual modeling as part of the conceptual model. It's not captured. And also the interrelationships and the constraints that you put between the classes is not captured that much. So the constraint language included in terms of model-based engineering is what I'll talk about a little bit later. So you can see the way that the information exchange between different stakeholders is multiple heterogeneous and conflicting interactions. And the models could be information model, it could be conceptual model, it could be physics-based model, or it could be data-driven model. Right now we are using AI and machine learning models that we are trying to understand the system from the data. So machine learning is nothing new. It has been there for a long time. Kalman filter is one of the starting point of, actually, if you look at it carefully, that is a machine learning way of looking at it. So the idea of model-based engineering or any of the systems that we are developing should be based something like we are trying to build an Esperanto manufacturing language for all of these people, so that they can formal language for system integration. The science of system integration is what we need to look at, how the systems can be put together. I personally don't like the word system of systems, because system itself is an abstract concept. But when you say system of systems, it doesn't make that much of a clarity. And where do you stop? Can you say system of, can keep on going? So I personally don't prefer the word system of system engineering. Standards play a very important role. So this is not only for system integration. There are many entities like interoperability, availability, security, so many other entities are there. I will talk only about interoperability as how standards play into this. I just highlighted the definition of INCOSE, and I'm going to touch on those: formalization, requirements, design, verification, validation, conceptual design models, and life cycle. So I already talked about that a little bit. I'll go through that a little bit more in terms of actual implementations. So the typology of standards are very important in model-based system engineering. So what is that we are trying to build using these models, and how they are going to interoperate? One is that the typology of the zero level is basically the programming languages that I already talked about. At the highest level is you want to make a computer representable and computational tractable. So there are different type of languages and scripting languages that you can use to represent what you modeled. So for example, in UML, if you did all of that, the mapping of the UML and binding it to a particular language is what many of this software does. The second type of standards are information modeling language. Many of you are already aware of UML, SysML, and all that, and including some of the semantically rich languages like knowledge interchange format, ontology languages, etc. And at NIST, we developed a description logic or first order logic based language called PSL, which is process specification language. It's a language for representing processes. So you can define using PSL, you can define your own language. It's like a meta language for process representation. And type 2 and 3, as you go more, you can see that we start talking about the actual domain of discourse. What is the content? For example, it could be about product information. If you're familiar with ISO standards, ISO STEP is one of the standards. Many of you may be aware of it. And you can see there are other examples that I have provided. And finally, how do you put it all together? So that's where I talked about the architectural frame standards like the Zachman framework. Zachman framework is a foundation on which many of these other enterprise architecture frameworks have been developed. I'll show you how we use all of these type of standards in actual manufacturing scenario. So just before going to that, I thought it may be a good idea to see many of these standards are developed by different people for a different purpose, and the content. Remember the mental model for these two people. They have their own way of developing the content, how they classify their systems, and how do they model it. So you can see the gaps and overlap between that. As you see on the x-axis, I put all the life cycle stages. On the y-axis are different focus. Are they focused on product? Are they focused on process information? Are they focused on enterprise services? So that's where we are. And this is one of the problems, or maybe even an opportunity for model-based systems engineering to look at it. What is that we are trying to build? And there's no silver bullet here. And MBSE is one of a tool. It's not like a silver bullet where you can build systems purely based on MBSE. You have to bring in different perspective to that. So just to give you an idea, if you want to really drive deep and then from like a Google map and zoom into a particular standard, and you can see the overlap here. How the system engineering concepts and product lifecycle support standard, which is an ISO standard, or kind of have the same idea, but they model it in a different way. So that's the problem here. How do you, your model is as good as my model. So that's the problem we need to understand how model-based system engineering can help. So model-based engineering approach as applied to manufacturing, I'll just give you a slight idea about model-driven architecture. Already other talks have introduced the meta models. So I will skip this slide and go directly into that. So if you look at model-driven architecture, starting from the actual instances to the M1 level to all the way to M3 level, if you're familiar with this, it's something like if you go beyond M2 and M3, there are languages for defining languages. So it's something like meta modeling for the way that you want to define your domain of discourse. Suppose I have a language for describing product, and then I have developed a modeling language at the level of M2 and M3. So then you can use that as an overarching language so that everybody uses, and then the concept and clarity and constraints are all similar. And model information computing is actually domain-specific modeling, as I already talked about in terms of manufacturing, or it could be rail system, or it could be healthcare, or it could be bioinformatics, or anything that we are applying model-based systems engineering. And then I'll talk about the actual model for smart manufacturing as we go along. So there are different types of programming interfaces. I don't want to get into too much details into this because there are the software systems available. The way that I look at them is, you look at the meta programming interfaces, format specifications, and how you translate that to domain-specific languages, the model integrated programming synthesis, and different application domain. So for example, if you look at manufacturing meta model, or it could be a from that you extract, define your own manufacturing model, and then you can have a different focus on application domain, for example, in terms of predictive analytics and machine learning and AI. And then you use that for visualization and scoring of your machine learning models. So, so now I covered those three things. So now I want to get into sustainable smart manufacturing. How am I doing with time? I want to speed it up based on the time. Neha, can you tell me how much time I have?
Yes, you have around 12 minutes, 12, 13 minutes. Yeah.
Good. So that's very good. So let me talk about sustainable manufacturing. If you're familiar with it, please bear with me. Otherwise, if it is a new information, I would like to get your feedback. This is nothing new. This has been going on for some time. I just want to put it visually for you to understand what are the different types of modeling at the macro level and the micro level. The macro level is we are talking about, we start digging things from the earth, whatever we use, whatever we eat, comes from earth, mother earth, and then we make them into products, and then we use them and throw them. The use and throw idea of manufacturing products have created a huge problem for us. And then you can see the climate change issues, etc. So what they call the triple bottom line is, how do I look at people, planet, and profit, and as a close concepts. So if you look at what the industrial revolution happened, you produce more, that creates more jobs, you sell more profit, and more jobs. So that kind of a linear thinking has created this issue. Most of the problem was we have resources, and the resources are infinite. And if you don't have resources in my own country, I'll go and grab it from somewhere else. So that's how we have been doing for the past many years. And we are running out of that. But now you can see the effect of emissions and other things related to manufacturing. So industrial, there are three, if you look at the three buckets of emissions: industry, building, transportation. So you can see that the major portion coming from manufacturing. So if you want to, for example, if India wants to become a manufacturing hub, they need to think about two things. Where are the resources? How am I worried about what are the impacts of using those resources in that local community? So the modeling of this is life cycle thinking, and systems engineering problems are very, very complex. So in terms of manufacturing of sustainability is basically, most often when you talk to any manufacturing person, they worry about three things: cost, quality, and throughput. Faster, cheaper, better. But they never talk about greener. I mean, how good these products are manufactured. Not only that, how good these products will be in use. So in sustainable manufacturing is focusing on how good you are with respect to resources. So now, why am I talking all these things? Because we have to model all of this. How am I going to model this in terms of systems engineering? One of the open problem in model-based engineering or anything that we do is classification. Classification is an open problem. There are no mathematical structures for defining classes or how you define your classifying or taxonomy that you're building. So there are some mathematical structures like category theory. Category theory is one of the basic foundational mathematical objects by which you can define many of the other mathematical ideas. So I'll talk about quickly these three things and how models are helpful in this area. So first is, how am I developing this taxonomy? Remember that I said that different producer and consumer have mental model. How those mental models have to be captured in a domain of discourse. So ontologies provide a way of capturing that from different tools. For example, CAD, PDM, PLM tools. I already showed you in the beginning how these different models and mental models have to come. So in terms of product has form, function, behavior. So how these ontologies can be built as an interaction in system modeling, so that when MBSE people are coming, they already have a clear-cut way of understanding what the concepts are, what things are modeled, what is your system parameters. All those things are conceptually designed and defined so that you don't need to define in a conflicting way. So that's one of the problems of interoperability. It starts breaking down here. If you don't do it well, the rest of the things will not work together. So I'll show you another example in terms of material information model. So if you take a simple particular aluminum type, if you start from material engineering, they have a coupon and they have a test sample, and they do this and then define the models in terms of how this property structure of the material. Okay, at that level, it's a completely micro level information of how this phase transition of this material will happen. How can you shape it? What kind of issues we'll have with respect to your atomic structure, etc. But if you go along in the information, you can see the chemical structure, test methods are all the ones that they are worried about at that level. But if you look at the engineering level, we are about the macro level information. We are talking about yield strength and etc. So you can see that a simple manufacturing information itself gets complicated. How MBSE can help here? Can it help? It's not clear because it's very complicated problem in terms of how you apply this. Similarly, if you take a process information, actual manufacturing process, whether it is casting or die casting or 3D printing or any of that, you can look at that the unit process and then how this is an IDEF type of diagram. So input, output, and constraints and the resources. This has to be modeled in a way not only at the information level, but also at the mathematical or physical model, science-based model to this. So I'll show you some of the ideas of that in terms of smart manufacturing. So before getting into smart manufacturing, we need to understand what this analytics and machine learning is all about. One of the problem is every manufacturing problem is now being converted into machine learning problem. It's not. Machine learning is just a tool. We are using it to predict something. That's about that. So we need to bring science to that. Otherwise, you are only doing regression. You're not doing causal relation. So if you look at the modeling, starting from the actual system and simulation of your real world, and from the data, how you understand the system better. So I mentioned Kalman filter. When Kalman filter system is identified, you know already the mathematics behind it. But in data analytics, they don't understand the physics, but they simply put a relation between input and output. Okay, that's where the system will start breaking down if you don't bring the physics to the problem. So there are different types of things. So for example, descriptive is what happened. One thing, things didn't work, you want to understand what happened. It's something like a diagnostic, why did it happen? And predictive, below predictive and prescriptive and cognitive is where we are moving towards. What is called a stronger AI, a general AI. Can I explain my results of AI is what we are looking at in manufacturing. Otherwise, if you're going to make a major decision based on this analytics, can I explain this? So the causal inferencing can be done or not is the question that we need to answer. So this is where the final architectural languages comes in. I told you about typology. This is typology 3. So if you start from the simple at the highest to lower level is physical systems, Internet of Things and industrial Internet of Things, sensor devices, PLCs, SCADAs, etc. And then if you go all the way from to shop floor, and then we create data and then models, and then finally optimization models or control system models or predictive models, and finally business models. So the vertical ones are all those type of standards that I already talked about for interoperability, security, all of that cybersecurity issues, a major problem for this. So how MBSE can also incorporate cybersecurity as part of the systems engineering is one of the challenge, I think. So the forward problem is, if you do all of this.
I'm sorry, sir. I'm sorry for interrupting you. Only 5 minutes are left for you.
Fantastic.
Okay?
So yeah, good. Thank you for reminding me. So if you look at the forward problem is basically, if you do all of this, you can do these things, reduce cost, improve quality, etc. But the inverse problem is what we are also interested in doing systems engineering. For a given level of, suppose the plant manager comes and tells you, reduce your water consumption by 20%. How do I do that? This is called synthesis problem or inverse problem. Can systems engineering provide that kind of understanding. So let me talk about a few things here. The data, for example, from the data, what can you learn? So you can learn how can I predict quality, that is produce product right the first time. Okay, you are reducing waste. Okay, that's one of the top 5 reasons people are applying industrial Internet of Technologies. How good are my resources? How good I am using my manufacturing assets, machines and machineries and all of that. So predictive maintenance is one of the things that people are trying to do. And then finally, the overall resource efficiency is what we are looking at. I already talked about this in the previous slide. So how do you bring both this science-based model and the data-driven model together is what I call science-infused machine learning for causal relation. So the standards, I am the chair of the ASME VNV 50 standard, and Yoga is part, he has attended those things. If anybody is interested in joining ASME VNV 50 standards, please let me know or contact Yoga, he can help you with. For more projects in smart manufacturing, please visit this website. As you can see, a lot of projects, and you can also look at the roadmap that we developed as part of these ideas. So let me just quickly go through some of the ideas. I want to touch and feel, this is not just we are talking in the air. We have actually developed some of these ideas. What is the meta model repository will look like for manufacturing? What kind of predictive modeling languages that are automatically generated? So how you bring in, remember the mental model of an analytics person and the mental model of a manufacturing person, how it can come together is what we have done in the real world. So this is at the M0 level, this is at the M2 level, and this is a intersection between those two domains. And then we also have a model library, the meta model library, that is a language for defining your manufacturing process. And then we also developed a language for data acquisition and data visualization. All of these interoperate. So I'll show you the meta model at the manufacturing level. So you have a process. We've used if you look at this, the double parenthesis, the reference, it's a meta model coming in instance of meta model coming from a manufacturing model library. And I don't want to explain all these things. The constraints here, what this closed diamond means, etc. So you can see this actual representation of that in a language, and language binding into a particular language representation that allows you to not only model supply chain level, factory level, process level, and different types of flows. And then we actually generated a predictive model using many of these standards. If you are interested in, please refer to the standard that we have developed. So this automatically generates from the process model using a state transition diagram. It generates a neural network model, and I don't want to get into the details of that in the lack of interest of time. And this particular software is available, and not the software. This is a proof of concept model to show that yes, you can actually do this type of problem, but there are lots of issues in this. The computer tractability, the expressiveness, all of that are still a problem. If you want to do a causal inferencing, how much of computational complexity is there? And verification validation has to be the one important thing. I just want to build, all of that have been done, but how do I know that how credible these systems are? So we need to have verification validation. So I don't want to get into the details of this too much, because I can give a talk separately on the VNV because it's a very important concept. So if you look at that, we talked only about mathematical model. Now we are adding empirical model and the data analytics model for verification validation. We are still figuring out what do you mean by validation if you don't have the physics of the problem. So how do you incorporate the science into this so that you can have a causal relation? So this is what I mentioned about ASME VNV 50. Please contact Yoga. He can help you with it if you want to join. We are looking for people who can contribute to this. And then I'll skip this. So closing remarks, there's a close connection between languages and domain of discourse. We need hybrid models. I already emphasized that a few times, causal inference, better design. All this modeling and everything is fine, but can I do a model repository? how can it define model library, model life cycle? If you do a modeling, how to retire that? How do I maintain that and retire that model for model reuse, etc.? And we already talked about. So I want to close here, and this is a book I strongly recommend. Julia Pearl, if you know Julia Pearl, he was the one who started Bayesian networks, and his son, if you remember, he was assassinated in Pakistan by terrorists. And anyway, I'm digressing. The Book of Why is what he developed something called 3-level hierarchy, starting from association, intervention, and counterfactual. And he classified present-day learning machine learning is only at this level. We are not even at these 2 levels. So we have to be very careful and mindful of this. And we are not having a silver bullet in terms of how model-based systems engineering have to evolve in terms of all these issues in manufacturing. So I'll stop here and I'll take some questions if you have any.
Yes, we have. So, as we see, there are specific views frameworks like UF, which are used in manufacturing domains. Are there any?
I lost you for, what is that?
Okay. Are there any specific views frameworks like UF, which are used in manufacturing domains?
It's a very broad question. I don't understand what views are, because there is architecture framework that we have used. We have developed a modeling language for that. If you want to go more details into that, there is a website you can go at NIST, or we use something called Generic Modeling Environment, GME, which was developed at Vanderbilt, funded by DARPA, for how specifically you define viewpoints for manufacturing. So we have developed it at NIST. It's called Product Ontology for manufacturing things. And based on that, industrial ontologies have been developed now. So if you Google industrial ontology, you will get that.
Okay. Thank you, sir.
Sudarshan, I have a question. You were here. Yeah. So I'm just trying to play the devil's advocate here.
Yes.
You presented model-based, you definitely talked about the pros and cons, and you're indicating that we have a long way to go. Now, is models the right way of doing things, or should we look at some different paradigm altogether? Because, if you see MBSE, people have been talking about, but it is not widely used in the organizations, but then a lot of talk is still there, and everybody is doing good work around it. They are showcasing things, but then there are a lot of issues still to be solved. So are we, looking at something, okay, maybe that is the way to go, or should we go to a different direction altogether?
Yeah, that's a very, very good point. And I've been following UML, SysML, and all this MBSE for some time. And unfortunately, I stopped working in that area in the past 6 years, because after I moved to DOE, my things have completely changed. I totally agree with you in terms of the problem-solving capability of MBSE. People are looking at MBSE as if it's a tool. MBSE is mainly a way of organizing your thoughts. So if you only keep it that way and then understand how these models have to interoperate, how do I make sure this integration can happen, what is the system thinking, then you have to bring in different type of disciplines into that. What is the domain of discourse? What kind of modeling language that are specifically designed for the particular domain of discourse? And then use from that to develop your model, and then understand what are you trying to model. Is it an information model? Are you doing a conceptual model? Are you defining a modeling of the mathematical model? Are you doing a computational model? Are you using a machine learning model? So depending on that, you have to understand how MBSE is used. Most of the MBSE examples that I have seen so far is software engineering, and how far they have progressed. I'm not keeping tab on that. But in the real engineering world, like manufacturing, it's still not there yet.
Thank you, Sudarshan. Yeah, that clarifies.
Thank you, sir, for your wonderful talk on the topic.
Okay, thank you very much. Thanks for your time.
Thank you. So now we will go with our sponsors lightning videos. I would like to invite Mr. Paramjit Singh Bhatia from Collins from Collins Aerospace. He is a director of engineering, having a master's degree from IIT Kharagpur, having more than 30 plus years of experience. Over to you, Mr. Paramjit Singh.
I think you have to enable my video. I tried enabling it. Okay. There.
We can see you.
All right. Are you able to hear me all right?
Yes, clear.
Okay, great. First off, thank you for giving us this time slot to come and talk about our company as well as about model-based systems engineering, which is the topic that we are all out here talking about this and discussing, brainstorming, and learning from each other. So what I would like to do in these, I believe I have 15 minutes, is that right, Kalpesh?
Yes, sir. Yes, sir.
What I would like to do in these 15 minutes is to give you a quick overview of what our company is about, what we do, and who we are. A little bit about that in the first maybe 5, 7, 8 minutes, and then about model-based systems engineering, what we are doing at Collins Aerospace, and how we are progressing on our journey, on our digital transformation journey. Let me know if you're able to see my screen.
Not yet. Please give it a try.
Okay, once again.
Hey, Yoga.
How about now?
Oh, thank you.
Perception. So I like your that mental models. You know, I keep talking.
Yeah, we are able to see your screen.
Sorry, Dr. Yoga, can you mute yourself?
Your real world or your mental model, right? So,
Yeah.
And that is what makes sense. So that slide was really good. So I don't know how many
That
people,
was a quick
Always, can you mute others?
Understand, because what I have seen from yesterday is, that they are still in that small domain of, making models, making a C code, and, execute it. And that is the MBSC.
Yeah.
Right? So,
sorry for this
so much
disturbance.
more that I hope they understand with all these talks that there is so much more to do.
Yeah, and most of them have done only the software engineering,
Software engineering.
Yeah, that's all they have done, but if you remember, I think we talked about this in
Vivek, are you there?
One of our discussion, I remember, even Donald Knuth, Don Knuth,
Vivek?
Hello.
the guy who wrote the Art of Semi-Numerical Algorithms, the volumes on computer science.
Right.
He wrote.
Okay. Sorry for this disturbance. My apologies.
Yeah.
We will extend your time, sir. Please go ahead.
No worries. Are you able to see my screen?
Yeah, able to see your screen.
Okay, great. All right.
Thank you, sir.
Yeah, no problems. Okay, so as I was saying, I've divided my talk into two parts. Well, the first part is where I want to give you all a quick glimpse on who we are, what we do, and then move on to what's happening in our company. Where are we headed in terms of digital transformation and model-based systems engineering? So let's get started. The slide. All right, there. So Collins Aerospace is part of Raytheon Technologies. Raytheon is a multinational company headquartered at Waltham, Massachusetts. We are with over $74 billion of annual sales. This is the 2019 numbers. We are one of the largest aerospace and intelligence services providers in and defense manufacturers in the world. We have more than 190 plus years of combined innovation leadership experience, and our research and development teams are creating breakthrough technologies in fields such as artificial intelligence, advanced propulsion, electrification, and thermal management. We have close to 61,000 engineers and scientists. They are all spread across the world. They are all leaders in their respective fields with great technical depth and breadth across key research and development areas. Our company has a strong focus on R&D, and you can see that from the amount of funds that we commit on an annual basis. We commit close to $8 billion on an annual basis on company and customer-funded research and development. We serve customers in the commercial aerospace and defense industries, combining complementary technologies, offering world-class engineering teams to deliver innovative solutions. So that's about Raytheon Technologies. That's the group company. Moving on, Raytheon Technologies has four different companies under the umbrella. The first one is Collins Aerospace. That's the company I belong to. Collins specializes in advanced structures, avionics, interiors, mission systems, power and controls, and we serve customers across commercial, regional, business aviation, and military sectors. The next company under the Raytheon umbrella is Pratt & Whitney. Pratt & Whitney designs, manufactures, and services the world's most advanced aircraft engines and auxiliary power systems for commercial, again, different sectors, commercial, military, and business aircraft across the world. The next one, Raytheon Intelligence and Space. The Raytheon Intelligence and Space is involved with disruptive technologies, for our bringing disruptive technologies to our customers to help them succeed in any domain against any challenges that they may be facing. We have advanced sensors, cyber services, and software solutions that help provide decisive advantage to civil, military, and commercial customers in more than 30 countries. So that's Raytheon Intelligence and Space. The last one is Raytheon Missiles and Defense. It's involved with the product, producing a broad portfolio of advanced technologies, including air and missile defense systems, precision weapons, radars, command and control systems, delivering end-to-end solutions to detect, track, and engage any kind of threats that may be coming in. Let's take a look at Collins Aerospace. That's the company that I come from. Collins is a unit of Raytheon Technologies Corporation. We are leaders in advanced and intelligent solutions for global aerospace industry. Collins was created in 2018. When UTC Aerospace Systems and Rockwell Collins, when these two companies came together in 2018, that's when Collins was created. Combined capabilities involve, a large area of capabilities in the commercial, military, and business aviation segments. We have a global presence with over 78,000 employees spread across 186 customer countries, annual sales $26 billion, and headquartered in Charlotte, North Carolina. Let me also tell you a little bit about the Collins Aerospace strategic business units. Collins includes 7 strategic business units. These are formed to meet the customer needs in specific areas and segments, and once again focused at bringing innovation, the latest technologies to serve our customers in these areas. The first one here, you see, mechanical systems. Mechanical systems is based out of Charlotte in North Carolina. The products include landing gear, actuation, propellers, flight controls, pilot controls, hoist and winch, and cargo systems. The next one is mission systems. The mission systems business unit is based out of Cedar Rapids in Iowa. The mission systems business unit is involved in creating solutions for secure military communications, navigation and guidance, missile actuation, simulation for training, and helping the Air Force to conduct exercises, instrumentation, strategic command and control systems, unmanned aircraft systems, electronic warfare systems, and ejection seats. These are some of the products that the mission systems strategic business unit provides. The power and controls business unit, it's based out of Windsor Locks, and they are responsible for producing electric systems, engine controls, air management, and airframe control systems. Aerostructures, based in Chula Vista, California. The products include nacelle systems, flight and control surfaces, naval composites, and other structural components. Avionics is the next one, is one of the largest business units out here. This is once again based in Cedar Rapids, Iowa. The avionics products include, cabin management, avionics systems, all of what what the pilots use in the cockpit to fly the plane safely. So that's what the avionics business unit produces. There is a new business unit that has been recently created, which is not reflected here. It's called Connected Aviation Solutions. This business unit is based at Annapolis, Maryland, and is involved with the advanced analytics, comprehensive digital capabilities into predictive maintenance using the large amount of data that's generated today by the aircrafts and the airline industry. Secure network communications between ground to air, air to ground to ground, ground to air, and all of that. So those are the last one is interiors, and that's out here. Pretty much everything that you see in the interiors of an aircraft, from seating systems, evacuation systems, galleys, galley inserts, lavatories, life rafts, things that you see and things that you don't see. There are some things that we hope that you never see, things like oxygen systems. Those are deployed when the cabin pressure drops, and we hope that we never have to see those systems, but they have to be there. So those are the products that the interiors business unit is involved with. The company has Collins Aerospace has a strong legacy of innovation. As you can see out here, several of the founders have been innovators of their time. Sir Arthur Collins, on whose name the company is formed. And then there are others like David Sundstrand, Thomas Hamilton, Benjamin Goodrich, Fred Rohr, Pauline Rathier, and so the company has a strong legacy of innovation, and that continues, till today. So that was the first part of my talk, where I wanted to give you a brief overview of our company. The second part I wanted to cover the digital transformation that we are at the we are going through this transition. It's
Hello, sir.
I'm
Sorry to interrupt.
Yeah.
Sir, you left with 2 minutes.
Oh, left with 2 minutes.
Yeah.
Okay. I thought I had 15 minutes.
Yeah.
No worries. Okay, we'll go a little faster. So that was the first part. The second part, as I said, I wanted to cover very briefly the digital transformation journey that Collins is going through. As you all know, aerospace and defense companies are facing several challenges in systems engineering processes. And one of the biggest challenge comes from managing document-centric approach or systems, where we are faced with managing a large number of requirements, very complex integrations, thousands of suppliers and parts coming in from thousands and thousands of suppliers located across the globe. And then, of course, the last but not the least is the challenge of meeting the regulatory compliances. So these are some of the challenges that the industry has been facing, and there has been a desire in the past and current to hasten the development cycles, cut the development time, and bring products to the market faster than what has been done in the past. There's also a push to move from a document-centric approach to a model-centric approach. That's what the previous presenter was also talking about, the model-centric development cycle. So that's the push. That's the direction in which Collins is also moving. While we are embracing and moving in a direction to have more and more model-based engineering, I would like to cover also the digital transformation, which goes beyond just model-based engineering and kind of it integrates the entire product development life cycle and provides multiple benefits. And we'll just look at what we at Collins are seeing in as benefits at 4 layers, the incremental value that we hope to get from a digital transformation. So at the product life cycle level, there is this whole digital engineering, model-based engineering, Industry 4.0, and digital, aftermarket, digitizing aftermarket services. All these 3 things coming together is something that's helping us bring products faster to the market. Speed of development, it also helps us grow, expand our margins. So that's what we are seeing at the product lifecycle level. When you go down to the data and software platforms level, there's a large amount of data that's getting generated, and we are increasingly working to bring this data, use it as a strategic asset, not just to increase visibility and create a connected ecosystem, but also to create value-added solutions for our customers. One of the very successful solutions that Collins Aerospace has created using data is the Essentia platform, which is a predictive platform helping the airlines to predict failures before they happen, and make the repairs and the replacement of parts well before the parts fail in the field and lead to aircraft on ground kind of situation. So that's what we are seeing as a great value add at the data and software platform levels. At the business integration and optimization level, it's more about efficiency and productivity. In the past, what we have done is manually taking data, taking reports, and artifacts out of each of these systems, like the PLM system for engineering, the MES system for manufacturing, the CRM system. So pulling out things manually and then sending those where they are required, that has been done in the past, but increasingly the integration and streamlining of workflows at this level is all about efficiency and improved productivity. Last layer, that's about the digital foundation. And this is, again, something that's helping us improve the employee experience as we move into a more digital, more connected kind of a framework. There is opportunity to show our employees, for example, let me take an example of a designer, to show our designers the view of a technician in the field or the people in manufacturing. It's a great amount of value for them to be having those views. They can learn, they can see how the products are being used in the field and how the products are being manufactured, and take all of that feedback into the next generation designs. I know I'm short on time, so I have one last slide, and this is my last slide. This is a little bit more about model-based systems engineering, what we are doing at Collins. And I won't go into the design and development part, which is something that a lot of the other presenters would have talked about. But I just want to highlight a couple of things that we are doing at Collins. If you see on the left-hand side of the slide, the pursuit to order capture, that's an area where we are using a model-based approach and this is very early on in the development cycle. This is where we are working with our customers to understand their requirements, to get their requirements and size them up, come up with a very high level of architecture to see whether, what will it take to build that system and go into bidding. So it's these are reduced order kind of models that we use out here to do certain optimizations that we are able to do in terms of cost, weight, performance out here very early on, and engage with our customers. So that's something that we have done successfully on the air management systems on the A320X programs. So that's something that I wanted to highlight on the left side. The other thing that I want to highlight is on what is there on the right side. When you see the produce to deliver and service and support side, here we are using the models. We are combining the models that we have created with data that you get from the field, which is something called model correlation out here. And what this is one of the examples as to how this is helping us is something that we faced with the brake control system.
Apologies to interrupt, sir. Sorry, we are above time.
Yeah, this is the last one. If you have another minute or two, this is my last slide. Okay, so I just wanted to close this with the example from brake control systems, where we were able to solve certain problems that were seen in the field, oscillations that were observed in the field. We were able to get the data from the field, do model correlation, do the root cause analysis, and find or pinpoint the problem to the hydraulic fluid contamination. And when we went back into the field with that root cause analysis, it was fixed in no time. So that's something that I wanted to highlight. Like I said, this is my last slide. Thank you all for the time to present out here. Anything else that we need to cover before we close this?
No, sir. Thank you. Thank you very much.
Thank you, sir.
Right.
Thank you so much, sir.
Yeah. Thanks for sponsoring the summit as a gold sponsor. Thank you.
Platinum.
Thank you.
Yeah. Platinum sponsors. Yeah. Now I would like to invite our sponsor to Mr. Paul, who is the Vice President MBSE Solution at MapleSoft. Bharani Raj Mohan, who is Project Manager at MapleSoft. We would like to welcome you, sir.
Thanks a lot. Can you hear me?
Yeah. Yes, we can hear you.
Okay. Okay, so Bharani's going to share his screen, and I'm just going to give a bit of a high-level introduction to MapleSoft and you know what motivated us to develop Maple MBSE. I should also point out that we're working very closely with Binary Semantics and BlueK in the Indian market. I'll talk a little bit more about that at the end. Okay, we just click next slide.
Sorry to interrupt. You'll be having 10 minutes for the talk.
Yes. Yeah.
Thank you.
So the in our work, it's very interesting from the previous presentation, that V process. We work very closely within that V. We have many analysis and modeling and simulation tools that help engineers to make design decisions. MapleSim, I noticed, wasn't in that in that slide. Perhaps Pramjit, we can talk about how we can get MapleSim in there. But in our projects, one of the things we're observing in terms of the interactions with the systems engineering process, that there is actually a bit of a communications problem. We have our traditional customers who are using our tools to feed information into the systems engineering process, and that led us to develop Maple MBSE as a tool to help in that process. And the way we do that is to be able to give all of the various stakeholders a tool in which they can be used for to accelerate the introduction of MBSE within the digital enterprise. And we do this by providing a way of, actually, can you stay on that one for a moment? To provide a way of introducing consistent engineering content and knowledge into the systems model, but moreover, to help to reduce the sort of inertia or the organizational resistance that typically happens when you start introducing new processes. So you click the next. That this not only helps in engagement between the various stakeholders and the systems engineer, this actually helps all the various stakeholders to be able to work together through the systems engineering systems model in order to capture the specific knowledge and share that across different stakeholder groups. Click again, and fundamentally it reduces project cost. So a lot of that friction is removed between the various groups. That reduces errors and disruption to the project, minimizes budget costs and overruns, and then increases the likelihood of project success. And this has been demonstrated in many of our projects that we've been involved in. And click next. Next. Okay. Yeah. So how do we do this? So Maple MBSE is basically an Excel front end with a layer that provides a synchronized bidirectional connection directly into the systems model. So what the end user sees is a task-specific view that can be used to capture information from the work that the end user is doing, and then submit that information back into the systems model at the appropriate level of detail, but in a consistent structure that is expected by the systems engineer. Click next. It's a familiar user interface. So we're not dealing with having to teach people, systems engineering tools or SysML or Capella. They just simply use Excel as the way of being able to view, enter, and modify system information that can then be submitted into the model. Of course, there are many different use cases for this. If you think about the range of activities where Excel is used for for engineering work, you can understand that we need to have a very, very flexible way of being able to customize the user interface to capture the different tasks that we can use for Maple MBSE. And click again. And at the moment, we offer integration with most of the main standard platforms, IBM's Rhapsody, Magic Draw, Cameo, the system modeler, and we worked through their Teamwork Cloud platform. And then last year we introduced an adapter for Capella. So that's really just a very high level introduction. What I'd actually want to do really is just set this up for Bharani to give you a live demonstration, just to talk you through the workflow in doing this. So over to you, Bharani.
Yeah. So I already have Maple MBSE open and it is connected to model in Teamwork Cloud. On the title bar of Excel, you can see that I am connected to the Teamwork Cloud server. I've opened a project already here belonging to a certain branch and the revision. So as Paul mentioned, the way Maple MBSE works is it's not an import or an export tool. It always have, it's going to always have a live connection with the Teamwork Cloud server. So the way Maple MBSE works is we have something called as a configuration file. The configuration file is what the user can customize to query different types of model elements to get different information the user can interact with and save it back to the model. So when you launch Maple MBSE and connect to a server, based on what you have defined in the configuration file, Maple MBSE will access that part of the model. It is going to transform that model and add that information in an Excel interface. So Excel is just a front-end interface that the user is going to interact with. The main advantage of doing this is, as again, following back on what Paul mentioned, you have system engineers who are comfortable working with the modeling tool, but there are different stakeholders or experts who are familiar only with their specific domain, but you need information or you need them to review or contribute to your MBSE process. So this is where Maple MBSE is going to help them. Based on the different views, example, you can do requirement traceability, you can define a system hierarchy and so on. So in this simple example, what I'm displaying here in this worksheet is it is showing me the different components that's in the model and the hierarchy of those components. So for example, this is a model of an hybrid SUV. This column here is going to list all the components that's in the model. The column D is going to show if that component has if it has a subcomponent, level 2 subcomponent, and so on. The interaction is pretty simple. It's going to be same as how you're going to interact with an Excel. Say I want to add a new component and a subcomponent relationship. Let me create a component called wheel bearing. So what this will do is it's going to create a component, and I want to add the wheel bearing to be a subcomponent for the wheel hub assembly. So I'm just going to use copy paste and assign that wheel hub assembly is going to have a subcomponent called wheel bearing. The next line appeared automatically because you can already notice that wheel hub assembly is owned by the chassis subsystem. So this is how your interaction will be. Each worksheet, you can consider it as a view into the system model. So for example, this worksheet is displaying specifically one single component, which is the power subsystem and its subcomponent. You can bring in different aspects of the model, different views, different types of model element. Example here, component, their interface, what are the different value properties, default value. Finally, again, for the same power subsystems, I'm displaying the function, what are the functional flow, how it is being connected to each other. System interface, this is specifically the internal block diagram in your SysML model, like the components, or the interfaces, the matrix with a check between the intersecting cell. So this means that the accelerator with an interface ACC is connected to the power control unit and so on. You can see that how easy it is for a user to interrupt a SysML model. So what I'm going to do is I'm just going to save my changes to the server, and we will see how these components are being reflected in the SysML model.
Sorry to interrupt. but you're over the time.
Oh.
Let me just update this and show how the model is being reflected, and this will complete our session. So this is the SysML model here. So I have the model already defined. Here in the containment, you can see the wheel bearing appear here. So this is the model that we just interacted with and the component that we created. And you can easily see the link and everything is being captured as SysML elements itself. So this is how MapleMBSE works. And with this, we will conclude our presentation.
Yeah. All right. I think we're done. Thanks very much.
Thank you. Thanks.
If anybody wants to find out more about us, we actually do have a webinar in more detail with Dassault Systems on May 25th.
Yeah, I have seen your LinkedIn post, and please do tag Incoze India so that others can also able to see it. Yeah.
Okay, thanks a lot.
Thank you. Thanks for your gold sponsorship for this summit. Now we will go for a break for 2 minutes, and post break we will start with our panel for the day. We will meet at 6:35 sharp. Hello everyone. Welcome back after a break. We have a panel of the day. I would like to invite Mr. Ajay Tukral, Principal of System Engineering at Raytheon Intelligence and Space. He will act as a moderator for the panel. Mr. Murali Krishna Menon, Site Leader in Fusion Preparation and Delivery, Becton Dickinson Technology Campus, India. Mr. Saket Kulkarni, Associate Vice President at Agiliad. Mr. Suraj Kamath, Systems Engineering R&D Function Head at Philips Mobile Surgery Business. We are waiting for our another panelist, Mr. John Anderson. He'll be joining us soon. So over to you, Mr. Ajay.
Thank you. Can you see the screen?
Yeah.
Okay,
yes,
great.
Ajay.
Okay, good evening, everyone. So we have this panel discussion related to MBSE application in SE practices, and our focus is on the medical device development. And when we had talked among our panelists, we were trying to understand what is the best way to understand how MBSE is being applied in SE practices. So we would like to understand that. So our panelists have put some few presentations together. What we'll be doing is first we'll have the presentations, maybe about 5 minutes each. And then once all the presentations are done, then we'll go into the Q&A part. To just get going on this one, just to kind of lay a background, and this is nothing special or new, it's just I always like to bring the background a little bit in focus. What we are talking about is product development, and product development has got all these life cycle stages. You start from concept and all the way to retirement across. So this is a typical picture of what different phases and stages are. And we are doing systems engineering all across. And as we have experienced in our traditional approach, where you have documents and other, what you would say is non-MBSE based approach, there are some challenges. And the question is, does MBSE really help us? And how is MBSE helping? So both those questions are coming up. Okay, MBSE has been in the market for almost 20 years. How far has it achieved? How far has it gone? How has it been applied in medical device industry? What are the pluses and minuses of it? So you would like to understand that piece. And the panelists will be talking from their perspective, from their experiences about how they have applied MBSE. This picture, same picture like the previous one, but it more or less emphasizes on, as you look at the different stages, you could see what is happening, that there are different teams of people working. If you really think about it, when we are doing any development, there are people always involved. You have the digital aspect, your technical aspects that are happening, but people are the you could think about as the individuals that actually make sense of all of these things that is happening. And you can look across this picture what is happening. There are different groups of people working, you would say, collaborative fashion. So what does it really mean? How do you bring this collaboration? If you go into the traditional way, in spite of all the digital aspect, also you'll see that the exchange across these different stages are not very smooth. So this aspect of MBSE and the digital thread that comes in terms of unifying things is critical to it. And we would like to understand that. Again, we are talking about, I've heard the previous couple of presentations in engineering side, the same problem, be it aerospace, automobile, healthcare also is no different. We would like to understand that. We would like to keep our discussion interactive once we have our presentations complete, and just to get some key questions out among our folks who are on this call, maybe have some questions, or at least give them some idea about what kind of questions we are looking at. So with that, I would like to first invite Murali to present his viewpoint on the MBSE applications.
Yeah, sorry to interrupt. Before we start, I would like to take a chance to welcome Mr. John. He has joined now.
Thank
Welcome,
you.
sir. Yeah.
Thank you.
Please do continue.
Thank you, Ajay. This is Murli Krishna Menon. Ajay, will it be okay if I share my screen?
Oh yes, sure.
Yeah,
stop.
Sure. Let me know if you are able to see my screen.
Yes.
Okay. Great. So I thought I'll take a minute to introduce myself. Right. I'm primarily a mechanical engineer with end-to-end product development and systems engineering expertise in healthcare and industrial domain. Of that, about 19 years plus in healthcare domain specifically, right, and about a year in industrial domain. Right. So in my career, right, in healthcare, right, I've been and lucky to work in across multiple domains, right, ranging from diagnostic equipments to therapeutic product development. Started with ultrasound scanning machine design, then MRI scanning machine design. Worked on oncology therapy planning systems, MRI based, MRI assisted brain surgery system. Right, the first concurrent PET and MR simultaneous scanning system from GE, right, etc. Right, as part of my career, right, and I've been associated with multiple companies, global MNCs, all into healthcare, like GE Healthcare, Medtronic, and now BD. And the product ranges, right? I mean, I've just included some snippets of the different products that I worked on. Been in positions of principal systems engineers, engineer manager, managing systems engineering team, hardware, electronics, and mechanical team, and currently I'm the site leader for infusion preparation and delivery systems, and I'm also the focal for systems engineering and innovation. Architecture and innovation team based out of Technology Campus in India. Yeah, that's about myself. Now let me jump into the topic, right? So I've primarily, right, categorized the content that I wanted to actually spend on, where MBSE has helped personally me and my team, right, and in the view of healthcare product development, right. So I've seen that, okay, before this session, right, there were references of the V model. So I would like to actually reference that V model and explain in the context. Some of the details, right, I'll not be able to put it across with lot of data points, because like some of them are confidential. So I have kept it quite high level. right? So that will not have any IP related issues. Right. So where I mean, in healthcare perspective, right? I mean, the dotted line box that you see, right? That's the area that I have actually been benefited with applying MBSE related elements, right? Whether it is we are talking about technical risk identification, right? Or understanding the system requirements all the way to the design outputs, characterizing the design space, the system interactions, right, etc. Right. So if you look at it, right, though I have actually capped the risk-based approach at the end of the design transfer in healthcare, right, it doesn't stop here. So I have just mapped out the area that from a design development space, right, what we typically focus on. So in healthcare development, right, risk is about everything. It is important that whatever design that or the product development that we do, it doesn't lead to any undesired effect in terms of hurting the patient, right, or caregiver in that process, right? So it is important that we understand the right requirements, right? We have the right architecture to support the development of this requirement to achieve the same, right? We'll have to have we should be able to verify this design also very well, right, to make sure that we are generating objective evidences to prove that the system is safe, right? So for that, it is important for us to understand a lot of the interfaces that we have, how the interactions happen between the subsystems, right? And the subsystem could be, right, different components coming together. It could be various domains coming together, etc. Right? So essentially, right, in this process, right, this is where the MBSE wise, right, I have been benefited in terms of system development and performance characterization, right, translating the system requirements to the functional elements, defining the performance related elements for the functions, right, and making sure that that the system is behaving or as per the intended use. So in this process, right, I've also been able to clearly define what the verification criteria could be, right, to challenge the design, to meet to prove that we don't have any residual risk. We are truly meeting the requirements, right? Well, right. So I've also been able to leverage some of the effort, right, on MBSE to come up with good challenging verification criteria, boundary condition, system performance prediction, etc., to say that yeah, risk wise, right, it is within control, right? Now on from a maturity perspective, right, there is a lot that MBSE could potentially do, right, from a complex systems development perspective, right? And today I don't think we are there, right, but hoping that, right, as we proceed further, right, the design verification element, right, if we are able to predict and without much of hands-on verification, right, we are able to get to the design verification, prove this that the system is truly risk-free, right, with the help of MBSE tool. That will be ideal future state that I foresee, and I do see progresses happening in that direction. It's just that today, if you ask me, are you there, right, I will say no, right, it is still further down the line. And this could be applied whether it is a new product development, it could be a systems engineering, right, where once you have infrastructure set up, right, we could take more confident, more data-oriented decision, right, for executing on the programs. So now, just to give a snapshot of what I have done with MBSE, right? So I was responsible for developing something greenfield kind of a product development, right? Wherein the high-level system functionality wise, right, we had to use multiple harsh chemicals. Some are acidic, some are basic in nature, right? And this was used for disinfection of a component. So the measure of the outcome was not a direct correlation, right? It had to be actually correlated to a outcome, right? Which is resulted in because of multiple interactions coming in place. So it was an indirect measure that we are talking about, right? In like though there are chemical volumes and flow rates that we are talking about as input, right? Outcome is measured in terms of microbial disinfection. Then chemical neutralization for safe disposal was under purview, which was also again handled by the same system. Multiple state machines synchronization, right, to actually achieve the function, right? That made the system complicated, right? And then multiple sensors interaction for successful control system implementation was at scope. So why we decided to go for the path of MBSE is because, right, we wanted to have a early risk rate prediction. Right, we wanted to mitigate, plan the risk mitigations early in state, and also confirm that these risk mitigations that we are planning is truly effective, right? And what it led to is that ultimately, when we are talking about handling harsh chemicals, we ended up with the help of the MBSE tool that we implemented. We ended up avoiding exposing harsh chemicals to the associate who were working on it, leading to some cost saving in terms of the chemicals, like logistical challenge reduction, handling of these chemicals, right, disposing of etc. from an environmental perspective as well, right? And effectively, we saved about 7 months of development time, right, because of this. Now, from further down, right, we also were able to leverage this to have a early software robustness, right? We were able to run the system, right, with the help of the MBSE model that we had, right, to have end-to-end continuous run operation kind of scenarios, right, looking at memory leaks and other potential interaction related issues, right, and early in the game, and we were able to resolve them early in the design development stage, leading to a very robust system design, right? We also ended up using it for optimization of time constant related impact, typically, which otherwise you will not get to know a lot of these things, right, until unless you do a end-to-end hands-on product development test runs, right? So how did we do it, right? We did it with custom characterization setup, right, with the help of a yeah.
Would you be able to summarize your point?
Yeah.
Because we have other. I would like to have people asking more questions. Thank you.
Yeah. So it's almost done, right? So the setup that we did, right, it was with the help of a non-standard tools that we used, right, for closely integrating with the development platform, because we had a state machine based setup already. We didn't want to reinvest in development methods. So basically, we used the functional PWAs or boards and LabVIEW-based sensor input, combination of empirical and first principle based models that combined together, integrated with the actual software, right, which is based on the software, the state machine based approach to achieve this kind of setup, right? So that's all I had from what I want to share, Ajay.
Thank you, Murali. And now, could I ask Suraj to present his points?
Yeah, sure. Hello, everyone. I think Murali has set up a context for the usage of MBSE. Let me share my screen. I won't take a lot of time. So let me know once you can see my screen. Okay, cool. So, I won't go into deeper into MBSE and a lot of systems, but I think everybody is aware of the current situation with the COVID scenario that everyone is facing, and I think we are already knowledgeable enough to understand that most of the hospitals have been requiring a device which is called as a ventilator, which is used for basically providing auxiliary support for patients, right? So what has happened because of that is, like, everybody is trying to make a ventilator. And the reason why I wanted to bring this context here is, I think when we're doing products under, for different domains, we have really good engineering background, and we know what is the implications of who are the users, and a lot more clarity. But when we come into innovating healthcare products, I think there's a lot of urgency sometimes that we end up pretty quickly trying to produce a prototype or a product. And in the last couple of years, we have seen a whole bunch of bandwagon of product manufacturers across different domains trying to jump in and try to make a ventilator product, right? So the concept of the challenge with that is we are looking at very short-term solutions. Complexity of a product like a ventilator is not just to produce a product and then launch it in the market, but also to make sure that it is useful throughout its working life. And that's what is so important when it comes to medical devices. So of course, the consequence of something that you bring it into the market and then you're not able to support, is very dangerous for the end users. The reason why I wanted to bring this context is, unlike very mature industries like automotive, where we have years and years and decades of experience, when it comes to healthcare, we need to look at not so much as the solution, because we, as all of us are engineers, most of us, we try to look at the solution. We are trying to look at, okay, what is the current problem? What is the quickest solution? And at the same time, we also look at the commercial valuation of the solution. So the biggest challenge is not the solution. The biggest challenge of system engineering is the complexity that we are working across when we're making a product, right from the concept all the way till manufacturing, serviceability of the product, and more importantly is where the product is going to be used, the environment, the patients on which a product is used, who's going to be the users, that is our surgeons, the nurses, and so on. I think the focus of engineering is always on the product, but less on the user. So the difference in between medical devices and other industries is how do we focus not only on the product that is a system in scope, but also focus outside the system, the environment in which the product is used. And that's the challenge. So we have to look at who's using a product, what is the risk, what exactly is the problem, how is the product getting used in the environment, and the product has to work consistently. It has to work on day 1, it has to work on day 10, it has to be easy for manufacturing, it has to be easy for servicing, and that's what brings in the complexity. What we're discussing today is how do we manage this complexity? Because if you're just thinking about the system, the subcomponents, the verification, validation, which is all engineering requirements, we somehow lose track of or lose the user in concern, or we don't understand the problem very well. So I just had these 2 slides just to bring in the context where MBSE could actually help us in reducing the complexity, and not only from an idea, but all the way till all the stages of manufacturing, which Murli has just covered. And at the same time, it will cover a lot of things post-manufacturing service throughout the useful life of the product.
Thanks, Suraj. I would now like to invite Saket to provide his viewpoints.
Sure. Thanks, Ajay. Just in interest of time, and also because I don't have a slide, I'll just maybe give a context in a few minutes. So basically 2 high-level things which I want to talk about. I'll give a 1-minute background on what I have done in the past 19 odd years of my career in medical devices. So I've been working mostly on imaging devices, X-ray based devices, CT, X-ray, flat panel X-rays, C-arms, cath labs. That's my background. And I worked on end-to-end product development and releases for India as well as for global markets. So for me, the context of model-based development, model-based system engineering development, and where I've applied it is mostly in the latter half of the V, more in the validation and the verification phase, where I feel it is very strongly helped in in the overall non-dependent testing of most of the system release work. Those are the few examples probably I can help to relate and talk about in the following part of the discussion. And the second aspect I want to bring is predominantly because of the function of image quality and software which I've predominantly worked in. I feel the integration of MBSE and the scaled agile way of development, which is not just limited to software now, it is probably adopted more as a system development perspective, wherein right from the requirements to the design to the verification validation, in the entire aspect of development, how do we bring about the MBSE as well as the scaled agile framework into picture, which I think is going to be the way it moves forward in the years to come. And probably not to contradict, but to sort of supplement the point which Suraj made, that just like it happens in automotive industry or which is of course more mature in adopting a model-based development. I think the healthcare industry also needs to go in that way. I understand it's more compliance-driven, regulation-driven, but still I don't think there is any a vastly different way of applying those regulations, which cannot be done in the healthcare industry, and which unfortunately is way lagging behind right now because of the non-accelerated way of development, as well as not really doing it in a scaled agile way in the true sense. So the software aspect of MBSE is what I think I want to bring in this discussion in the next half. And any questions or any discussions around that, I would be very happy to get into a discussion or try and answer those. So Ajay, that was, I think, a few minutes of this introduction and context I wanted to set from my side.
Thanks, Saket. And I would now like to invite John to share some few viewpoints from his side.
Yeah, will do. So let me share my desktop. So basically, I have been working with medical devices my entire professional time. So I've been doing this for roughly so do you guys see my presentation?
Yes, John.
Yep. So I've been working with medical devices my entire professional lifetime. I've been part of the army for some time, and then when I took a degree in computer science, I ended up in medtech domain. I worked with different cancer therapy procedures like the Elekta machine or the HemoQ or SpectraCure or Dignitana, and recently I worked with a mobile operating table for patient positioning during surgery, minimal invasive surgery. And what we discovered there was that everyone who works with medical devices have regulatory challenges. I think we can all agree that the regulatory has become more and more demanding due to normal causes, and it takes more time and so on. So what we discovered here is that by adding MBSE to our development stages, from usability to product realization, we cut in our normal product size roughly 300,000 euros in cost. And that is mainly because of less rework time and understanding regulatory needs from the start. And we used MBSE on all these aspects, right from requirement management, modeling the requirements into an architecture that we understand, and all these meetings about how will this actually work. We could just bring up the Capella model and say that this is how it's going to work, and everyone got on board on that. And we did also a quite a big extensive work with educating the certifying body, the notifying body, in how to actually read these types of data models, and the result was that we scrapped a lot of questions from their side by them having the possibility to actually drive the model and understand the product themselves before testing. In content, by working with risks and usability and design on the system model level, we managed to cut costs greatly. So that's my take on it. I'm not taking more time for that, so I'm here to answer questions if there is anything.
Thank you, John. So, so thank you for the viewpoints. So, before we get going, on these about MBSE, let's just make one quick point. So, MBSE is a method of doing systems engineering. We have been doing systems engineering, and things have changed to not change, but I would say now it accommodates model-based systems engineering. Now the question is how is MBSE really helping us, and what are the challenges? When we talk about MBSE, it doesn't happen by magic and it starts solving all the problems. You have to apply yourself in a proper way to use MBSE. And then there are tools, and the tools have their own feature sets, their own challenges. The tools also are, I would not say they're quite well developed at this point, but they're getting there. And then you have systems, the SysML language is there, which is also, a new released version will be coming out soon. I think it's the end of this year, something like that. So things are still evolving. That's not that things have been finalized. So for the panel, as well as for the people around, I think independent of medical device, I think these are very common questions when you're doing your product development and creating a working and successful system. How does MBSE, what are the challenges? Not, I could see the value of MBSE, but what are the challenges? You bring some systems engineer in. Do you think he's ready to apply it? When you start applying MBSE in your product development, what happens then? What are the other things you are trying to do to make MBSE work within the context that you're applying for? So those are the kinds of questions I'm more curious to understand, and we can focus on that. Maybe there's a training, maybe there's a workforce element to it. So all those different pieces are also part and parcel of this MBSE, this new methodology. All right, so with that, I'm seeing a couple of questions out here. Let me see how I can get the chat questions out here and we can step through it. Sorry. Give me a second here, sorry. Okay, the first question comes from Vivek Chandra. He's asking Murali, as you mentioned that medical industries are not yet to MBSE, what according to you are the challenges in implementing MBSE? So that's a pretty relevant question. When you start applying, what are the difficulties you face when you apply MBSE? Could you share some of your thoughts on that, Murali?
Sure. Thank you, Ajay, and thank you for that question, Vivek. Right. So from a challenge perspective, right? I mean, I'll go straight for the biggest challenge, that is convincing the regulatory agencies. right? As medical devices, right, we directly come in touch with or contact with the patient, right? The applied parts, I mean, has additional consideration, right? And that is something that the regulatory agencies look very closely, right? If you and geographically, right, different countries have different regulations as well, right? If you look at China, right, for example, right, they the Chinese regulations, right, they don't until unless they test it out by themselves, right, they'll not accept, right, a lot of the test data, right? If you look at FDA, right, I mean, compared to where, I mean, maybe 10 years before, right, when you look at analysis being, even analysis as a method for verification, right, was not being accepted, right? Now, if you look at it, right, I mean, it is acceptable method of verifying some elements, right, of your design. But the thing is that, right, you need to rationalize it really strong, right? You need to make sure that, or give the confidence that, okay, you're not missing out anything, right? You're not leaving anything for the chance, because we are talking about touching the patient, right? So how do you convince or use these models to convince the regulatory agency will be the biggest challenge that I would say, right? Now, is it impossible? Right, I will not say that it is not impossible, but I think still, right, from an acceptance perspective, right, I mean, we have a journey to go further, right? So that is what my response would be for that.
So Murali, when we talk about this FDA and looking at patients and bringing the aspect of patients into understanding whether the product is working properly or not, and you mentioned about models, do you really need models? Have you used models to help in some of these?
So the fundamental element, right? I mean, I'll take it back to the critical thinking, right? I mean, let's not try to force fit every element, right, in there, right? But where it makes sense, right, it could be applied, right? So I think that is where the critical thinking element of a systems engineer comes into picture, right? Where we can apply and where we cannot. Right. So I've been part of organization wherein, right, a digital twin has been developed for the patient body, right, body part, right, critical organ, right, and where people have been developing and trying to make the element, right, which I mean, more consistent, more reliable, which can be leaned on for answering some of these questions, right? So now it's a long journey, right? I will not say that yes, today I've done that and I've been able to successfully convince a regulatory agency. That will be a wrong claim, right? That's not something that I will say is we are still yet there. But I think future-wise, right? If you ask me, right, do you think we can do it, right, for relevant area where we think, right? I mean, it can benefit. I think it is a possibility in future, is what I would say.
Okay, thank you. Any comments from other people? Any things to add from anyone?
I can add on to that.
Go
ahead. So I fully agree that the training of the regulatory body to understand how to use this and read this is fundamental. We did a lot of training with them to get up to speed, but in the same time, you never know who's going to be on that side, on that organization to be a third-party certifier. So it's a long journey, and I also agree that you need to look at the critical aspects of it. And to tie on to one of the other questions, what we did was also that we implemented how to verify different designs straight into the model by attaching the requirement to the model element and the ways to verify it. That's how you try to push it into one kind of documentation. So that was our way forward. Thank you.
Suraj, you wanted to add something?
Yeah, I just wanted to add, Murali covered the external challenge, right, coming from regulatory requirements. Medical device industry is completely driven by I mean, you need to make sure you have enough evidences, both for the inputs as well as the outputs for any design. I think that is what is driving what also John mentioned as a documentation requirement, just to provide that we have traceability and we have a lot more clarity on how decisions have been taken. Having said that, I think that's the external view. The internal view is also that we are in healthcare and especially in medical devices. There's also a lot of legacy. There's a lot of history behind the way we have managed requirements, the flow down of requirements, the testability and the verification validation. I think that's we've been doing it for decades in a particular way. With MBSE, we are trying to change it, trying to influence people to say, okay, is there a better way of doing this? Would there be any challenges? Like getting people on board. One's the set of people who are already doing it in a particular way. And the second thing is the specialities like electrical engineering, mechanical engineering, software, who have been doing things in a very, their own way of, SysML has come from UML. And they have a lot of way of working that they have been doing for so many years or decades now. And then we trying to change that is also one of the challenges that implementing MBSE as a methodology is really getting extremely challenging.
Yeah. Okay, great. Thank you.
And just one last point on that. Specifically to the point Murli mentioned on the verification aspect of model-based components. So I think where we need to really, marry the two things is as engineers, we just make sure that it works and I'm able to verify and then end it there. The SOPs have to be strong enough to give the right rationality, as you said, Murli, to make sure we take it to the completion that this is a method I'm going to use for model-based verification for a subcomponent or for a subsystem, and this is the documentation with the right SOP for the organization or for the regulatory body, which is going to qualify that. So if we take it to completion as an engineer or as an engineering team, then I think it will be really powerful to continue using this for larger and larger subsystems and subcomponents. Yeah, that's all.
Thanks, Saket. So maybe I can add a little bit of point to what all four of you have been talking about. What I heard is more or less on the verification side, and it's not just the medical device we are talking. Medical device is just one component, one piece to the system. The patient is on the other end, the healthcare delivery people are on the other end, and they also need to be sure that they use the device properly. So if you don't, I didn't hear from that angle, that perspective. You can give whatever, you can build any product, but the product has to be safe, usable. There are a lot of these different pieces, and just talking from verification is probably the most easiest part, and use of model is also a good way of approaching it, because clinical trials are very expensive and they should be used wherever possible. But the value of actual live trials is there because we are not there in the maturity of our own, how would you say, human models yet. So just need to be careful the limitations of what we have here. So, and I was, John, I had one question as you were talking about this regulatory piece, the training and all. Were you suggesting that the people on the regulatory side are still trying to accept MBSE? Is there a challenge in regulatory folks being more open to model-based approach? Is that your concern?
Yes, I would say that most regulatory or notifying bodies are very well acquainted with the traceability in Excel, and you got your requirement spec, and you got the risks, you got everything, and then you try to tie it up somehow in a spreadsheet that you trace back, right, and forward, or whatever way you want to slice it. That's what they're used to. And there is a lot of work with taking, like, this is the risk that you identify, and they look at that, and you look at, okay, what kind of mitigations has been done on that, and that's another document, and then you look at the implementation and the assessment if the risk mitigation has introduced anything new, and then you got a verification somewhere, and then you see that everything is linked up. And this can take minutes or hours, depending on what kind of how it's been documented. So they were open to understand the system on an early level, to understand these are the risks. You can see those as requirements into the model element, and you can trace that down to the code, and you can see the unit test result through the continuous integration check-in and so on. So, but by having this verification and everything tied into the model, we were able to shorten down maybe a 15-month lead time for a class B product down to somewhere around 6 months. Just by them understanding the system. So that was I think they are open to it, but they're still on a people-based level, not an organization-based level, sadly enough.
Sure. Okay. So thanks for that insight. I was curious about it. Thank you. There are quite a few questions, so let's move on to the next question here. So the question that's coming up is, any insights on applications or possibilities of MBSE in other healthcare area fields like drug development, prosthetics, and even healthcare delivery? Maybe I could just make a statement just from my experience. Yes, there are what do you call, a lot of medical companies doing work in this area quite actively. Hospitals are also working at it quite actively. I personally have some experience with Eli Lilly, who have been doing quite a bit in the digital engineering framework. So yes, it's going on, and you can ask around also. It's going on quite well. So the possibilities is, if we try to understand what possibility means, the tools are not specific to any specific application. They are quite general in some sense. So, sure. Next question. This is, I guess it's for Murali here, from Arvind. Just wanted to understand how MBSE helps to mitigate risks of development.
Thank you, Ajay, and thank you, Arvind, for this question. Right. So when you talk about risk of development, right? I mean, I would actually weigh in a lot more on the technical risk element, right? Which I mean, I will classify the risk as technical risk and program risk, though. Technical risk are program risk, right? But technical risk typically, right, are something that you can't typically just put in additional funds, throw in a lot of resources, right, and it solves it, right? Typically, you will have to work with the requirements, right, mitigate the risk, right, and it typically takes a lot more of effort in terms of figuring a way forward. Right. So the technical risk, right, is a significant area that I personally have seen wherein, right, could identify these risks effectively, right, in the past, based on the example that I mentioned, and which otherwise, right, would have been a slightly more difficult task, right, if you rely on conventional tools like FMEA and FTA, right? I mean, it's you're looking at just your thought process, imagination, analytically analyzing, right, and coming up with these scenarios. But MBSE, right, I mean, it helped me in terms of, okay, coming up with these insights more objectively, right, and could plan the mitigations well. So I would say, if your situation lets you do it, right, if the circumstance, because this kind of depends on what product you are working on, right? It is not a generic, right, blanket thing that you can apply across, right? So, but if your situation look you're in, or the problem that you're trying to solve, right, is conducive, right, I think this can help you mitigate the technical risk quite effectively.
So maybe I can add one point here is what is MBSE is if you think about, there are a couple of challenges when we are talking in this interdisciplinary thing. Communication is one piece, understanding is another piece, complexity is another piece. So these are common. And if you just try to think while you're working, just talking to each other and coming onto the same page as to what we are talking about, it's quite difficult. Having a tool like this MBSE method in the SysML language allows you to bring things together. If you do it properly, it definitely allows you to bring things together. And what that gives you is a power to make sure that you have not missed anything. The gaps are more easily visible, and you can it definitely helps you mitigate risk because now you can see the full picture much better. And there are team members who will be seeing the whole system, so it just helps everyone. It's a great tool for communication and sharing things. Can I move to the next question? If any other points from anyone else to add? Okay, next question. The development and safety regulations in healthcare domain is influenced from aerospace. So what are the practices can we draw from MBSE used in aerospace, and can some be incorporated? So personally, I don't know whether these safety aspects are coming from aerospace industry or not. I'm not knowledgeable about it, but I feel that product development or anything you're creating, these process of building something and making sure the system works for the larger public needs to be checked out properly. So yes, there are parallels. The question now here is what other parallels can we draw from MBSE used in aerospace, and can some be incorporated? Could you maybe I would like to understand a little bit more. What is it we are trying to look at the parallel? Are we seeing some gaps in the application? I don't know who asked the question, but I would be curious more as to what the full intent of the question is. I think there are parallels. Obviously, for me, I've been both in aerospace and medical. There are parallels. People are using it. To the degree at which we are using MBSE, both in aerospace, automobile industry, they're far ahead in the application. I guess it's because of the engineering aspect to it. But as you get to the healthcare side, it's a little bit slow on using some of these MBSE-based tools. And I feel that there's a difference because of the human element is much more stronger. It doesn't mean that the other engineering disciplines don't have human part involved in it. Other than that, I have seen both being applied in almost similar ways. They both go through a very similar lines of development in terms of understanding the system and putting the system together. I don't know if I'm answering the question right. If somebody else wants to add something, that would be good. John or Murali or Saket or Suraj, if you want to add something before I go to the next question.
I agree with you that I think there's a difference between a pure engineering aspect as in aerospace. Of course, you have a pilot, but in the end here you have a patient, and a lot of the regulatory requirements sits around the patients in terms of current leak levels and stuff like that, and biocompatibility and things like that. So I think it's a hard question to answer unless we understand more about. I think there are brilliant similarities, but also there are two different aspects to it.
Thanks, John. Maybe I'll take this last question, and what I would do is the remaining questions, maybe we can respond them later via email if that's okay with the team out here. let's just very quickly talk about the maturity level and very quickly, Murali, you want to provide one quick summary statement or something about maturity level?
Yeah, so I think I already touched upon multiple times, right? I mean, in the sense, right, it's still a long way to go, right? I mean, we are trying to use it in bits and pieces, right? In the manner wherein, right, we are able to manage out the outcomes, right? But I think we still have a long way to reach to the level wherein, right, we can truly use it for verification, validation, etc. Right? So I would say it is still at a nascent state, right? I mean, as how the complexity of the problems have increased in the healthcare domain, what the challenges that we are trying to solve with medical devices, right? I'm sure with that, right, with our continued perseverance and efforts in terms of looking at this, right, I'm sure we'll also make progress in terms of it. I know it is more of a philosophical answer that I've given, but unfortunately that's a state that we are in, and we have a long way to go.
What about you, John?
In terms of maturity, I would say that in medtech, systems engineering are well matured in systems engineering. Model-based system engineering, not much. I think it's very early days in terms of that, but with growing complexity and you want to connect things and regulatory requirements in different countries and so on. I think the complexity of the requirements needs something like MBSE to visualize the content. Thank you.
And, I think we are running out of time. If very quickly, one small sentences from Suraj. Do you want to do it quickly? Add one point on maturity.
Yeah, I think from a maturity point of view, it's completely a transformative way. So there's a lot of we're learning a lot from other industries. At the same time, I think the complexity, not only from a product development point of view, but also from medical devices, is multifold, because we're not only looking at systems but also the environment. So I was looking at some of the questions like risk management, residual risk. Those are things which are like very different in an OR, because we are not dealing with one product. There are multiple products that are used in an OR by different users, both trained and untrained. So there are complexities which are, I mean, when we look at from a product development, we are so focused on the inner side of an organization of what different functions are there. But I think the environmental aspects, something which is extremely critical. So MBSE is not a secret magic tool that will solve everything. It's definitely, there's a lot of different facets that we need to bring in right from the requirements, understanding the users, what exactly they are struggling with to get the right inputs. And I think that's will just augment the tools that we are using, and MBSE is just a process and a methodology that we will try to enhance and make products which are lot more safer.
Thank you. And Saket, just a minute or so, quickly, we can then wrap up.
Sure. So my last concluding remark would be that yeah, I think that the maturity is for today is still not there, but I don't think we have any option. We would have to go and jump on this MBSE way of developing medical devices, be it complex, not complex, purely because of the way it is going to be commoditized, like the automobile industry, for example. So we will have to treat it as an independent subcomponent, which MBSE will help to separate it out, and that is going to be the way forward. So we will have to get mature as early as possible. So the most mature player will be the leader.
Thank you. So Kalpesh, I'll hand it over to you. If we can get these questions, we'll try to respond them also. So
sure,
thank you very much, and sorry for excuse me for going over time. Thank you.
Yeah, that was a wonderful discussion, and we would really like to continue it, but because of like time limitations, yeah, we have to wrap up, but we'll share these questions with every one of you, and we'd like to have such discussions in future as well, because definitely there is not much discuss about the healthcare, and very few people know about it, and this will be a very critical area where we want technology to improve. That is very useful for the humankind and everyone. So with this, I would like to thanks all the panel speakers for taking your time and have such a wonderful discussion around the topic. Thank you.
Thank you, Kalpesh.
Thank you so much.
Thank you.
Thank you,
Thank
Kalpesh.
you.
Thank you,
Thank you.
everyone.
Yeah, over to you, Neha.
Thanks.
Thank you, Kalpesh. Thank you, everyone. Now, I would like to invite Dr. Ravi Rajamani, sir, for the talk 3. Dr. Rajamani, sir, is PhD, Formula Society of Automotive Engineers, Fellowship of the Institution of Mechanical Engineers. I would like to invite you, sir.
Hey, thank you. All right, I'll try and share my screen.
Sure.
Let me know if this works.
I can see you. I can see the screen, yeah.
You can see the presentation?
Yes.
Okay. I'm going to try and put this on full view. All right. Does that work?
Yes.
Okay, great. Hey, I'm going to change tax here and talk about model-based methods in aerospace. I'm not a SysML person, so I'm going to talk much more about general modeling. You can ask me questions later about specifics in this area. Okay, so model-based methods in aerospace. That's what I've been doing for many years. It's as everybody in aerospace knows, I know a lot of you here are medical, but certainly at this level, probably the two things are not that different. Throughout the life cycle of the aircraft, modeling and analysis are modeling and simulation are key, not only for the design, but also for continued airworthiness. What does continued airworthiness mean? Continued airworthiness means how to keep an aircraft in good shape so that it continues to work without any safety issues throughout its life cycle. So it's not just for the design and analysis, for the requirements, for the validation and the verification of design, etc. But it is also for the entire life cycle, throughout the entire life cycle. So models can be used not only for the initial part of this life cycle, but also for the following part. That's the main message of this. And we within the Neha mentioned SAE. It is not called Society for Automotive Engineers anymore. It's just called SAE International because we do a lot more in aerospace than actually we do in automotive side, believe it or not, in terms of standards. So SAE and others are doing a lot within this modeling and simulation area. I'll talk a little about that. I'll sort of briefly tell you what I have personally done with models in the aerospace area, not just for safety, but also for design. So as you all know, models come in very many different sizes and shapes. At the bottom here, you will see something called systems engineering models, which is what you guys are mostly familiar with. And that's, in my opinion, some of the most complex modeling methodology, because it actually uses elements of all other models. But really, the simplest models, you can call them simple, but they're structurally simple, but complex in terms of its the actual equations, etc. that go into it are the low-level component level models. We use them obviously a lot. System level models, you go up one level from there. And really, enterprise level models, which are the discrete event models that are used a lot to actually simulate the entire enterprise, are becoming much more common today. And we have worked at all these levels, and all of them are important. System level models themselves are not as common in the aerospace world today. I'm sorry, MBSE, in other words, SysML, UML, those kind of models, they're becoming much more common. One of the reasons, I think somebody mentioned this, was the certification issues, the safety issues. It's very difficult to bring those aspects into MBSE, but we are trying to do that. Anyway, low-level modeling, I know all of you are familiar with this. These use tools such as MATLAB, Simulink, etc. Here's an example of where we used it using for brake monitoring. And the idea is obviously to use all these aircraft parameters to estimate how brakes will wear, and using that we can anticipate when to stock up on spare parts. By the way, the whole area I'm going to talk about in this talk is I'm going to concentrate on something called PHM, which is prognostics and health management, which is really the diagnostics, prognostics, estimation of remaining useful life in a system. That's the key. That's the expertise that I have in my area, and that's what I'm going to be talking about. So all the examples you'll see are in that area. So this is at the lower level. Going up one level, we have enterprise level models. I'm sorry, there is a system level models, but also enterprise level models. Here is an example of what we did several years ago, trying to model the entire ecosystem, both on the operations side, where fleets are actually flying around, and on the maintenance side, where they're coming in for repairs. And we showed, and this was an exercise in actually demonstrating how prognostics, condition-based maintenance, CBM, can actually improve some of the key parameters within the within this enterprise. And we showed, for example, that by doing this, we could get specific advantages in terms of lowered lifecycle costs and increased asset availability, which is key to aerospace business. At even a higher level, you have what you guys are most familiar with, which is model-based systems engineering. I am right now working on a project with the University of Connecticut. These are my collaborators there, and with the BAE systems, trying to figure out how we can use MBSE in an aerospace example, where we can do a lot more of the optimization, the system level optimization upfront. As all of you are very well aware, as part of INCOSE, you know that making changes to a system upfront is much cheaper than trying to do it after the fact. After you've designed it, after you've validated and verified it, and then try to make changes, that's terrible. So we are trying to go even one step further back. Even at the concept level, can you use tools like Cameo, which is from CATIA and linked up with MATLAB and Simulink, to try and do a lot of this optimizations up front. At this point, we are still in sort of the first year of our research, so I can't say too much other than we are using software-defined radio, SDR, as a case study for this. So this includes all the electrical, the communications, as well as the mechanical aspects of this, to try and come up with a holistic optimization framework that will allow us to design a lot of the aspects of this upfront, rather than having to do it after the fact. So that's the use of model-based systems engineering, MBSE, in aerospace. Let me now briefly talk about what SAE is doing in this area in health management. I mean, SAE, as I mentioned, was established in 1905. And if you look at the number of standards it's developed about 32,000 standards in aerospace. And comparison, it has only about 8,000 standards in automotive. So it's really much more of a, I mean, I'm in the aerospace side of it, so I would say that it is much more of a aerospace standards organization than automotive, but still, obviously, it's in the entire mobility sector. So it has we within the health management community started, I would say, probably in 1975, in the 70s, was when this thing started with mainly with vibration monitoring for engines, and that is what the history of SAE's involvement with health management is. Now, obviously, we have a lot more in this area. We have a couple of new committees that have been started, and I'll talk a little more about that in the next slide. But in terms of what SAE has done for health management, not only has it set up a lot of these committees, but it's also published books and held courses, etc. So 3 new committees, well, actually 3 committees, with some of it concentrating on model-based methodology. One is that was started in 2019, is G34, which is artificial intelligence in aviation. This is extremely important, especially with electric aircraft and autonomy and all these systems. AI is becoming a very important part of aviation, and we are trying to develop standards within this committee to actually be able to certify these systems. So that's, as you can well imagine, is an important aspect of aerospace. The next one, which is even more recent, 2021, is G35, which is modeling, simulation, and training for emerging aviation technologies. Like I said, new aircraft, eVTOL, which is electrical, vertical takeoff and landing aircraft, EA, which is electric aircraft, and UAS, unmanned aerospace, aero systems, I guess, aviation. So those new aircraft, I think, will need to have a lot more model-based aspects to their safety assessment as well as their certification. This is a committee that takes that aspect, but also mates it with the training aspect. In other words, the same models will be used not only for the design and the certification, but also for flight simulation as well as pilot training. So that's kind of the idea here in G35. And finally, this is a venerable committee, S18, which develops some of the most well-known documents within SAE Aerospace, which is ARP. That should be 4754 and 4761. I apologize for that. These are anybody who's involved in SAE. I'm sorry, anybody who's involved in certification would be familiar with these. And the reason I bring this up is they are going to a lot more model-based techniques in the future, including MBSE. And there are other organizations besides SAE that are developing standards for certification as well as for aerospace design and verification, as well as continued airworthiness that are model-based. And EuroCAE, which is the equivalent of kind of SAE and RTCA within the European context, is developing standards in collaboration with SAE and RTCA in this area. RTCA, as some of you would know, is the developed standards for software qualification of aircraft software, airborne software. And DO 331 is a model-based, it's a standard for actually developing model-based methods for the existing DO 178, etc. So again, this is an alphabet soup of numbers. Names and numbers I can understand. If you are in this field, you certainly know a lot more about this than if you're not. ASTM is another organization that's developing standards and for model-based standards for aerospace in the normal category. Normal category are smaller aircraft, less than 9 passengers. So that's and certain weight restrictions. So that's where we are. And obviously the regulators are developing aerospace, I'm sorry, aviation circulars, advisory circulars for model-based methodology and certification. So with that, what I would like to do is summarize what I said clearly. Models are a key part of our what we do in aerospace. They exist at various levels. Like I mentioned, MBSE tools, specifically UML, SML, is not quite as common in this area as we would like them to be, but we are getting there. Co-simulation is important. I showed you how we did with MATLAB and Cameo. This thing is something that is will get better and better as there's more memory, there's faster processors, etc. Certification time and effort has to be drastically reduced. I believe personally that these tools will help in that. So this is something that we are working towards, and I'm sure you'll see a lot of papers, a lot of work in this research in this area, and it's only going to get better and better. Again, for the new crop of aircraft with artificial intelligence, with autonomous operations, this actually may be the only way of guaranteeing that these systems are safe. So with that, I'll end and open myself up for questions if there are any. Kalpesh or Neha?
Yes, sir. Let me check. I have to get questions from Vivek. Vivek, can you please pose the questions?
Yeah.
No questions is good.
Sorry, sir. This is Mudit. I have a question.
Yes, please.
I would like to point to your earlier slide where you talked about various layers of models or various different types of models. Do you see how do you see the interoperability between them getting developed in the future of what the future holds in terms of relationship between these type of layers?
Good question, Mudit. I am absolutely sure that that is the way these things will work. We have tried to do it. It's for example, in the CBM example, we mated MATLAB with FlowSim. I don't even remember. It was a discrete event simulator from. Yeah, I haven't used it in decades, so I don't even remember. But we tried to do that in this particular example. We are trying to do mating MBSE tools, Cameo with Simulink. I know that ANSYS has it's called the Phoenix integration system, where they're trying to integrate a lot of these tools to try and get different aspects, the discrete event simulations, model-based systems engineering, as well as deep analytical tools. Not to mention a finite element, CFD. It's going to be complex, but it is absolutely needed in the future. And I think it's just going to get better and better and better. Does that answer your question? Do you have any specific questions regarding this?
That answers, sir. And maybe if you have time, just one more question.
Yes,
your thought on mission modeling. I know it is getting a lot of hype these days about the mission engineering. So especially coming from aerospace and defense, I think this is important. So
it may be, but it is not something I do much of. So I don't know. I can go into too many details on that. If somebody else wants to jump in and talk about that. I mean, we used to do that a lot in at Pratt & Whitney, because that's the way we developed a lot of the requirements for our engines. It's not something that I've done much of at all.
Sure, sir. Thank you.
Thank you so much. Thank you so much, Dr. Rajamani, sir, for talking and so insightful talk on the model-based methods in aerospace. So thank you so much. Yeah.
Thank you for the invitation.
Thank you, sir. Now, I would like to call Professor Bhaskar Tamma, Professor in Mechanical Engineering, Mahindra, Hyderabad, and Dr. Arya Bhattacharya to talk on the topic MU Systems Engineering MTech Program Overview. I welcome you both, sir.
Hi, thanks, Neha. So, am I audible?
Yeah, you are.
Okay. Let me share my screen. Hope that should work. Okay. Is my screen visible?
Yes, it is.
Yes, sir. Yeah.
Yeah. Thanks a lot for staying so late and listening to us, and thanks for the invite. Professor Arya Bhattacharya is Dean Research of Mahindra University. He'll be joining me to discuss about this MTech program. Professor Arya comes with a lot of systems background, and it is his brainchild. So, but as department head, I'm just presenting the systems engineering, and we'll be very glad to take any questions and inputs on the program structure we have put together. There is always scope for improvement, and your inputs from the industry side and academics will be a great help for us, right? So with that, we'll move in. So there are requirements that we look at when we frame a course. One side is on the academic requirements. So typically we run the master's program for 2 years. Typical credits would be around, 60 or spread over 2 years, with at least 60 to 70% going towards lectures and 30% in projects. This would be capstone projects or the semester wise, and also the MTech project, right? So this the lectures would be a mix of core and elective courses. We have to go through the board of studies with experts from academics and industry who would go through that and see if there is a fine balance and meets the requirements of the program. Of course, the prerequisite we are looking for this particular program is an undergraduate degree from any of the engineering disciplines, and we are also sort of opening up for masters in math or physics with at least a couple of years in industry experience, right? The other one is to balance the course based on the industry requirements. What would be the role the system engineer would be playing, and what are the skill sets he would require. We'll talk about that in the next slide. And then what are the industries that we are looking for, and what sort of a careers these graduates, the master's graduates would be looking for, right? And the other thing that we are also looking at is to get the INCOSE academic equivalence. So it has certain requirements in terms of the membership. You have to do an MOU with the Indian chapter of INCOSE, imbibe the CBOK learning objectives, which I'll be talking about in a bit, and also the students who will be registering for this program and want the academic equivalency from INCOSE have to be members of INCOSE, right? So once they clear the required, meet the required learning objectives, and we submit the evaluation metrics and the grades obtained to the INCOSE. If they meet the requirements, they would be eligible to be associate of associate systems engineering profession, right? Which would be valid for 5 years with renewable available. And after that, based on how they perform over the next 5 years plus, they can then move on to be a certified a systems engineer professional and then be the expert. Right. So when we look at the systems engineering approach, right, there are different the V curve with verification, validation, and the different steps that it goes through, and the gate reviews that happen at each of these. It requires, interacting with different stakeholders, looking at both the technical aspect, the system level, and then how to build the systems, and then the utilization support, and how do you retire, right? So as a part of this, what would happen is it would require knowledge of multiple processes to be able to demonstrate the system engineering skills. The other aspect is as a part of going through these processes as a systems engineer, a system engineer needs to interact with different groups like marketing, sourcing, the research, engineering, manufacturing, and also interact with the leadership to get the requirements and then accordingly work out on the budgets, and then look at the entire system of making the product, right? While doing that, he would require different skills because it also means that how does he communicate, influence key stakeholders, work with management, have knowledge of science and technology, and also a particular sector that he is working in, like whether it is automotive, aircraft, healthcare, and other systems. Then he needs to know how the operational rhythm of the organization itself. And at the same time, also, have ethics on how to get the product to be a socially beneficial product, and how the products are built and what its final impact is, right? So ethics is really important part of the skill set that the systems engineer need to have, right? Along with the soft skills in communications, influencing management, the technical in terms of science, technology, and sector knowledge. So with this, these are, the system engineering interactions, the required skills, so it requires, people, process, and ethics knowledge, right? So the INCOSE academic equivalence requires a set of learning objectives, which are given on the left, and most of these are addressed through the document, the C-book, the Systems Engineering Book of Knowledge by INCOSE, right? So when we frame the coursework, we have to make sure that these learning objectives, right, are addressed, they are evaluated, and a particular benchmark qualification marks are established for a systems engineer, for a student to be given an academic equivalence certification as a associate systems engineer professional. And on the right is the general program information, where you look at, what sort of a rubrics or evaluation matrix, what's the coursework, what are the learning objectives. So this is the sort of, approach that INCOSE has, where everything is critically evaluated to make sure that the students have the required knowledge, has gone through the required evaluation process. So once this is addressed, right, the student did not take any further examination. So he has to just get the required credits in the courses of the program, and this will be submitted to INCOSE organization for their verification and certification. Right. So with this in mind, me, Professor Arya, we had Yoganand, Ramki from Honeywell. We talked to Professor Schneider from Cornell. We had a couple of other academic and industry experts. So with them, we put together a basket or a bunch of courses. So the core courses includes the Introduction to Systems Engineering, which would cover most of the systems engineering book of knowledge. So that with that and system of systems engineering, system analysis, safety, reliability, with this and the life cycle cost analysis, we should be able to meet the INCOSE academic equivalence requirements. Along with this, we are trying to include a few subjects related to machine learning, mathematics for systems engineering, project management, organization behavior, and engineering ethics, which are really important, as we have seen in the previous slide, in terms of the required skills for interaction and ethical behavior, right? And once these are the basic courses all the students would undergo. After that, if they want to get more in-depth knowledge in a particular stream or a group, we have a bunch of electives related to renewable energy, robotics, then transportation, which includes connected vehicle, aerospace, automotive. Then if they want to get more insight into the finance or supply chain or into ideation for entrepreneurship, we have those electives for them to choose from. Right. So to make these successful, there are a lot of enablers. We need the required faculty to teach each of these courses with experience in them. We also need industry experts who can talk about their experiences. One thing is teaching theory and sort of a few examples, so textbook examples is one thing, but the actual insights would come when somebody is actually working on a live project. This is where we are looking for industry experts to come in, share their experience, and look out for those finer points which cannot be handled through the theory lectures. And to help us, Professor Arya helped us to reach out to Dr. Kota and Professor Sudhakar from IIT Bombay and asked us to guide us. So they will be on our advisory board to guide us and bring in the required expertise. And of course, we are working with INCOSE to get the membership so that we will have the required academic equivalency program with the relevant syllabus. We also, looking for guidance, train the TED trainer, and guest lectures on current topics and trends in systems engineering. And actually INCOSE has helped us connect with Dr. David Schneider. He's the program coordinator for systems engineering at Cornell University. He gave a lot of insights, whether, do we need to do one course on each of the steps of systems engineering, or do we combine and give them a perspective so that the students will learn as they go along. So that has been a lot helpful for us in framing of the curriculum. Of course, Yoganand and Dr. Yogananda and Dr. Ramki have been, more than helpful to provide us the guidance in terms of connecting with the INCOSE membership, the MOU, their thought in terms of how the course could be. So yeah, with that, we are open to question. So Professor Arya, would you like to add some?
And no, not really. Actually, there was just a comment a few seconds back saying, when are you going to start your course? So we are starting our course from the academic, based on the 2022 academic year. That means it's starting from August, around middle of August of 2022. So that is the answer to that question. Next thing is that we have Professor K. Sudhakar. He's actually ex-IIT Mumbai. He's not in IIT Mumbai anymore. He was the HOD of IIT Mumbai, and I understand that they had actually tried to start a systems engineering MTech program, and I think it did run, I'm not too sure, for maybe a short while, but it could not continue longer. So we will actually also get the inputs from him. And of course, Dr. Kota is my ex-boss in ADA. So, we look forward to his guidance all the time. So Professor Sudhakar, we will probably get the inputs of why that MTech program or what are the challenges that may arise on the way. And we expect the inputs from him. Of course, Sudhakar is not here right now. But anyway, so we look forward to the support from him on that. And we look forward to the support from industry because we think this is probably, we want to make this MTech program in systems engineering a success. And it cannot be a success without the support from the ecosystem that prevails in India related to systems engineering, which includes government institutions like ISRO and DRDO, as well as private institutions. There are quite a few of them, mostly they're MNCs. So we would, so it is my sincere request to the various persons and groups working in these organizations to please work in cooperation with us, and we will try to work in sync with you for your requirements. And also, there's a bit of natural interest that our students who emerge from this course get properly settled in the corresponding institutions and companies. I can see a question, will the course be online or over a week? No, this is a full-fledged, see what we have planned as of now is that it is going to be a full-fledged course with students' residents. But if there is a lot of demand for an online course, we'll have to actually study that. Professor Bhaskar would like to comment on this issue of online, offline.
Yeah, as you rightly mentioned, we want this to run a couple of years to stabilize, look at all the requirements and strengthen the course. And then based on the strength, we'll be able to go online. Yeah.
Then there is another question, again a comment. How would this course be different for fresh graduates versus experienced professionals? So strictly speaking, we have, Professor Bhaskar had presented that the background requirement for this course is that one has to have an engineering degree. We have not set any years of experience requirement. However, for those who do not have an engineering degree like MSc in mathematics or physics, possibly one can expand these subjects. The question is that they will have to have a little bit of experience. So the whole idea is that the person who gets into this course, if he or she has got some idea of working experience, and the entire concept of systems engineering emerged from the functional processes in industry. That includes, say, for example, the research and development processes, the project management and project delivery aspects, and so on and so forth. So a person who has got a little bit of background in these will certainly be better. Now, the thing is that because we said that our course is going to be, at least initially, fully residential, we cannot make it conditional that the students who join will have to have years of experience in it. That's why we said that we can start with undergraduates also, undergraduate in engineering, who will be having some idea because they would have done some internship somewhere and also done some practical courses as a part of their curriculum. So just to answer that question, that is there going to be a difference? The answer is not really between experienced and non-experienced, say, BTech engineers, BTech or BE.
Because as Professor Arya has rightly mentioned, engineering graduate would go through the entire process from ideation to product. So he has some a significant background in terms of what are the fundamental physics, how do you take the basics and then try to design and build systems, right? So they can really appreciate once they join the master's program. So, and the other thing that we try to look at is use the first semester programs to bring everybody to the common platform and provide the foundation. So it's mostly about looking at the fundamentals of systems engineering, multidisciplinary optimization, bit on machine learning and other ethics. So such that they get, everybody will get comfortable, know what a systems engineering is, so that second semester onwards we'll be able to delve more deep into the individual sections of systems engineering.
So there is one more question. How the course will be conducted for working professionals outside the city where the university is located? So right now we are actually, as I said a little while back, we are not really looking at working professionals right now when we are launching the course, and we expect that it will be full-time students will be involved in this. But then after maybe a year or 2 years of experience, we will make it for working professionals, and then we'll have to we'll actually have to work out the details of how we can actually include as students working professionals who are not from Hyderabad city. I would just like to add a little bit more that, I will just, it is my request and it is our request from the university that to all of us, to all of those who are in this, as well as generally involved in the systems engineering ecosystem in the country, I think our country very much requires a good systems engineering program. And I'll request all of you to look upon this as your own program, not as Mahindra University's program. So far we have got a lot of help from Dr. Ramakrishnan Raman and Dr. Yogananda Jeppu, and of course Dr. Kota and Professor Sudhakar are our advisors. We look forward to their guidance, and we also look forward to continued support from the local, that is the Indian INCOs within India, and also to the people involved in different companies. So please look upon this as your own course. Please try to support this so that we can have a solid platform or foundation for systems engineering in this country. There is one more comment or question. How does Mahindra University wish to go about through GATE or any internship programs? I am not very sure about this question, but
I think it's about how do we do the admissions for master's program.
So Professor Bhaskar, would like to answer this?
Yeah, so the admission for this program will be, for people who have GATE scores, who are qualified and score GATE scores above a particular level, and those who have not, have scored higher, or they have not a GATE score, there will be a written test for a given syllabus. So if they get through that, then we will have the interviews, and based on that, we would shortlist students for the program. Does that answer the question?
So I would just, I don't know if Professor Kota is there, but if he is there, just a question. Would you like to say a few words about this new program that is being launched?
Yeah, I'm there. I'm watching the talk and all. As we go further, we have to see how to shape it. As you mentioned, quite some time back, Professor Sudhakar started an MTech course in systems engineering. It ran for about 4 or 5 years, but they were taking people with experience. People who have worked in the industry, or R&D organizations. And then they took them further. And basically, they were all aeronautical engineers. It was more aeronautical department which was running this course. But now you are rightly made it much more what you call broad based. And now the experience of MBSc and the experience systems engineering has been gained a lot more. So I do believe that you should do much better. But I have a feeling you should give priority to people with some background in industry or R&D or in an organization where undertake projects. Because yours is a MTech program.
Yes.
If you do for raw students who have no background at all, it is a challenge. This is what my understanding is. And also a lot of case studies, projects you have to build. Teaching what is there in the these books, what you have mentioned, is one thing that can be a starting point. But the biggest challenge is to build those case studies so that the students live through the project. That is what is important in this course compared to other courses. That is what we. Now that would need effort, and from the faculty plus industry people. And it should start, and we should not always talk about only aircraft and all that. We also should talk about simpler things, how we use systems engineering principles, right from needs based to the final product. I think we need to do that and build that knowledge base. And then at the end of the day, the one who is coming out of MTech must feel the whole subject. Okay, and they must do some live projects also as a part of your course. I didn't see that, but some live projects you have to take from industry, and you have to do that. So a lot of experimentation need to be done. But I do believe it's time now we run a course like this and make it a success. Okay.
And thank you very much for your words, Professor and Professor Kota. And actually, when we select students, I think we will take your advice. And we will try to prioritize students with who have got engineering degree, but also have got some experience, if we can get them on board. The other thing which Professor Kota said that yes, it will be very, very good if we can have live industry projects. And for that, actually, we need to, we have to kind of reach out to industry, but industry also has to interact with us so that some of the industries can take some of our students for actual maybe 1 semester or maybe 2 semester projects. So if you can get that support from industry, that will be great.
Yeah, as part of the master's program in Mahindra University, all are like, the final year projects, we would rather have it to be a industry-based industry internship project rather than doing something, in theory with us at the institute. So that's where we are trying to encourage more in terms of having them go for internships right from second semester onwards.
Yeah. So there is one more question now, that can there be any possibilities for e-learning? So, in the sense that the plan is to make it in the classroom, and of course we'll have projects also. But then there'll be a lot of information or knowledge which is not directly available across the board. So for that, we'll obviously have to depend on e-learning as well. But I think the stress will not be e-learning. E-learning will be a significant support for our efforts. That is what I feel.
And like Dr. Kota has mentioned, systems engineering is more about hands-on experience on live projects and all. So yeah, being in the class or doing internship would be more value add than e-learning. Yeah, that's my thought, but we will know as we go along.
Okay, so that was.
I have one more point to add for the consideration.
Yes, sir.
See, unlike in engineering, in management courses, there will be series of case studies, and through case studies, they teach the whole subject. I think that approach you may have to examine and see how to adapt it.
Okay, we will take the suggestion.
Yes.
And see how we can take it on.
Definitely. Yeah. Even Dr. David Schneider had a similar view. He told he could do a theory or, give a live project, and as they go along, they will be able to learn why a particular concept is important. So that has a more sticky factor rather than lectures. Yeah, you have rightly pointed out. Yes.
Yoganand here. Maybe another option would be to go for the DRDO also. Look at the government agencies, whether they can take interns. So like DRDO has MTech program across different institutes. This could be also, you could have sponsored candidates from DRDO attending this. And then you could have some mutual agreement where your students could go as interns there. So that is another point. Being in Hyderabad, you could perhaps approach DRDO labs there.
Yeah, thanks for the suggestion. We'll try to again activate this. That's a good idea, actually. We'll try to follow up on this. Maybe again for this, we'll have to seek support from Dr. Kota for his wide background in ADA and connections in DRDO.
Okay, sorry to interrupt you all.
You have to talk to them.
Yes, we'll talk, of course.
Sorry again to interrupt you all.
Yes.
But yeah, we need to proceed, and I understand this is very important conversation currently going on. And there is a lot of interest and demand for the system engineering curriculum or certification courses or the master courses. So definitely this will be a need of the time, and I'm very glad that you guys are working on it. Definitely you are getting a lot of support and guidance, and that is also a good thing. So we all will be waiting for rolling out these courses, and definitely it will be a huge success. With this, I would like to thank you, Mr. Bhaskar Thamma, Dr. Bhaskar Thamma, and Dr. Arya Bhattacharya for coming ahead and sharing your thoughts with everyone and making us aware about the course you are planning.
Thank you very much.
Thank
you very much.
Thank you very much.
With this last talk, now we are approaching towards the wrapping up session. I would invite Mr. Prasanna Ramamurthy, Secretary of Incoze India Chapter and Principal System Engineer at Collins Aerospace. Over to you, Prasanna.
Yeah, thank you, Kalpesh. So very good evening all. So it has been an exciting journey for past 2 days. And so we had a lot of eminent people, both from industry and academia, sharing their ideas and experience on current trends as well as the future trends of model-based systems engineering. And so the challenges and opportunities in adopting MBSE in various industries. So we hope this 2 days summit was beneficial to all the participants, both from the industry and academia. And I hope you all enjoyed these sessions past 2 days. So as an old saying says, all good things must come to an end. So we are finally here at the end of the MBSE Summit for 2022. So before we wrap up for the day, so I would like to present a quick summary of what we have gone through today. So yesterday we started with the grand opening with the inauguration of the main session by Dr. Kota Harinarayana. And so today we tried to sustain the momentum. And so we started our day with a mentoring session on systems engineering certification provided by Incoze. So as part of this, so we conducted a mock-up exam for the new certification aspirants who are pursuing the ASCP and CSCP certifications of Incoze. And so we hope it was useful for all of them. So we had a good number of participants taking up these mock-up exams. And so this was again followed by a panel discussion wherein we had invited people from industry who have already completed their certification at various levels, starting from ASCP to the highest level of EACP. And so they made time for this and shared their experience and the challenges and they faced during this journey, and so how they overcome. And so I hope this was useful for all the certification aspirants. So in going forward with their systems engineering certification journey. So after the SCP mentoring session, we had a career fair conducted by our platinum sponsor, Collins Aerospace, and so which received a very good response from the participants. And then in the afternoon, we had an interesting workshop on SysML version 2. And so Dr. Nikhil and Mudit, they provided a kind of orientation to the MBSE practitioners. And so they also demonstrated how the new version of SysML is better in terms of the providing consistency and expressiveness to the system modeling compared to their earlier versions. And so even this workshop was well received and appreciated by the participants. Then we started out with our mainstream session in the evening. And so this started with a brief overview about IEEE Systems Council activities presented by Dr. Ramakrishnan Raman. Then we got into the first tech talk by one of the invited speakers. So we had Mr. Tim and Mr. Kevin sharing their insights on adopting MBSE in the railway industry. So some of the interesting aspects that they shared are the relationship between the project management, asset management, and the systems engineering. So they highlighted the commonalities among these and also how they differ from each other. So that was really interesting to hear. And so they also highlighted some of the challenges in adopting the MBSE for the rail projects, like the stovepiping and lack of a clear digital engineering plan. So means I'm sure that these challenges are not just for the rail industry, maybe common for other industries like the medical domain as well. And so this was followed by another interesting session by Dr. Sudarshan. And so in his presentation, he really brought some radical ideas and thoughts, which could really initiate new debates on even the fundamental concepts of systems engineering. So in fact, his questioning of the real need for the concept of system of systems, and also so how useful the pure data driven analytical techniques for deriving actionable insights for the engineered systems. So these are some of the topics which would definitely trigger interest in the community and the participants who listen to his session. And so this was again followed by a presentation by our sponsors. So we had a presentation from Collins Aerospace, and so Mr. Paramjit Singh presented about how MBSE and digital engineering are transforming the business of Collins Aerospace. And so Mr. Paul from MapleSoft, so he spoke about how they are helping various businesses in adopting MBSE with their MBSE tools. And after this, we had an interesting panel discussion regarding the MBSE adaptation for the healthcare industry. And so here the key takeaway is that there is a long way to go in terms of introducing MBSE end-to-end into the healthcare industry. And so the panelists spoke about many challenges in terms of regulatory and approvals and certification. So while integrating MBSE into their development cycle. And they also spoke about some of the use cases where the MBSE methods are useful, especially for early risk reduction and also the effective verification and validation. Then, so this was followed by another interesting talk by Dr. Ravi Rajamani. So his presentation was a very short, but he shared his insights and his experience on how model-based methods are useful in prognostics and health management of aircraft systems, and thus to ensure the continuous airworthiness of the aircrafts. So finally, we had another interesting presentation by Dr. Bhaskar and Dr. Acharya regarding introduction of a master's degree program in Mahindra University on systems engineering. So we see this as a really a visionary step and need of the hour for the industry in India. And so we are hopeful that so even other educational institutions and the universities follow their footsteps and introduce similar courses in the coming days. And so we are really privileged to collaborate with Mahindra University from Inkose, India for introducing this course. So thanks for this opportunity. So finally, I would like to thank all the eminent speakers and panelists who enabled achieving the core objective of this event. And so we thank our sponsors, Collins Aerospace, Capella, Maplesoft, CTI, CADFM, ANSYS, and Honeywell for coming forward for supporting this event. And so I would like to thank our event partner, YDRA, Mr. Vivek Chandra and team for providing a great platform and putting all the pieces together to make this event a success. So our special thanks to Dr. Kota Harinarayana for his mentorship and guidance throughout this journey. And so finally, thanks to all the participants from the industry and academia for your enthusiastic participation and support. And so we hope this event was beneficial to all of you and interesting. And so in case, please reach out to us in case if you need any support from Inkose India or IEEE System Council for career mentoring or certification related queries or any topic related to systems engineering and MBSE in coming days. And finally, kudos to all our office bearers and volunteers from Inkose India, IEEE Systems Council, and AESA Design Division for their great coordination of the proceedings of this event. So with that, so we are signing off for the day, and we will see you all in the next edition of MBSE Summit. So have a good night and good day for the people from the other parts of the world.